and Huawei now is the largest company. So I have come from a small place. It's because I keep my eyes open and I go after what I want to do. And when I retired last year, I thought that I would work with my Indian colleagues, try to help. And IEEE provided me an opportunity. So I have been talking to many of you, sharing whatever little bit I know. So the photonics today, it is playing a vital role in our life. Whether it's healthcare, it's communication, it's economy, or environment, in social life. In healthcare, for example, even the massage, even you go there and you go physical therapy, they use 980 nanometer lasers, to massage, because this radiation is absorbed in some part of your muscles. So the healthcare is spreading everywhere. Communication, this presentation is possible because of the communication, otherwise it won't be possible. And the economy, whether it's your LED light or whether it's solar power generation, everywhere, the environment, the social life, you know that your smartphone, though you may be thinking it's a wireless, but it is not wireless. Wireless is only from the tower to your hand devices. The tower has to be connected to the core network. So the photonics is playing a big role, and it is expected that by 2024, photonics will contribute to like $1 trillion to the global GDP. I feel that India should contribute at least 10% to that, like $100 billion. And it's possible. That is a separate issue. The important thing to recognize that photonics is a multidisciplinary field. It is just not the photons. At my time, it used to be called spectroscopy. In physics, the specialization was spectroscopy. They used to teach atomic spectra, molecular spectra. So the photonics is a multidisciplinary field today, and it includes chemistry or physics and optics, electrical engineering, communication engineering, digital signal processing, and system engineering, digital to analog conversion, analog to digital conversion. So it includes everything. So even if you are a mathematician, you have a role to play here. This 21st century, it really belongs to photons, as the last century belonged to electrons. The important thing is that the photon itself, cannot work. It requires electron, to work with. You can see my screen. Can you hear, all of you? Can you see my screen?
Yes, sir. Yes. It's very well. Fine.
Okay. And you hear me? Okay. So yes. First question is, what is photonics? So the light travels as a wave, right? And that's called optics. When you manipulate the light, that's called optics. But when it interacts with matter, it behaves like a particle called photon. And the science and application of photon is photonics. And that includes generation of photons, modulation of photons, sensing the photons, processing the photons. Now the photon, it has no charge, it has no mass, but it has a lot of energy. And it travels at the speed of light, which is at least 1,000 times larger than the speed of electron, right? Electron speed could be between 10 to the 6 to 10 to the 7 centimeter, per second with under high electric field, but this guy travels at the speed of light 1,000 times faster. Electron interacts with inductance, capacitance, resistance of the transmission media. Photon doesn't have that problem. Of course, it can be absorbed, it can be scattered, it can be deflected, so that's a different issue. So it doesn't require much power. The attenuation, if you use the right wavelength, right fiber, there is very little attenuation. So the lasers or photodetectors, 2 devices, and now third device is the optical amplifiers, semiconductor optical amplifier. They all are just p-n junction, sophisticated p-n junction. Actually, if you know p-n junction, you can almost all the devices, because p-n junction is the fundamental building block of most devices, whether your solar cell, your LEDs. So all we'll be talking about the p-n junction, right? P-n junction is so important. So these devices are just a p-n junction with a sophisticated structure. Now, electrons and photons, they are natural partners. Photon cannot work by itself. To generate a photon, you need an electron. When an electron changes the state, a photon is emitted. And a photon is absorbed, then the state of the electron is changed. So they go together. Now, I showed a simplified diagram how the system works here. So you have the transmitter here, you have a laser diode. And to use the laser diode, you need a driver. And that is essentially the commissioning the signal which you have to transmit. It could be RF signal. I'm showing the digital signal here, a pulse here, but it could be RF signal. And transmitting the RF signal, it modulates the laser. So this is essentially an amplifier, It could be, to cover all the frequency range, and it goes through the optical fiber. By the way, you can be free space also. I'm showing an optical fiber because, but it could be a free space. And then you have a detector. And for detector, again, to get the signal, you need electronics here, a transimpedance amplifier, clock data recovery, and then amplifier, and you get your signal here. Now, important thing here is that I'm showing here digital, but it could be RF. But transmitting RF is very expensive compared to digital signal. Digital is very cheap. When you have RF signal means it must transmit as is, right? So you cannot live with any non-linearity, because then you will have harmonics, second harmonic, third harmonics, and you have to linearize components. So the cost of the RF system, analog system, you may find could be 10 times or 100 times. So if you have a system like this, the cost could be $1, per gigabit. Now, pay attention to this second chart here. So these are the different wavelengths, and this is the attenuation, and you like to transmit where the attenuation is minimum. So here, the C band here, that is 1550 nanometer, the attenuation here is the lowest, 0.23 dB per kilometer. And that's where, the third window, the maximum systems in the world, they use this band, which start from 1530 to 1565 nanometer. So C band. But then other bands are open. Before that, S band, L band, and this band here, it turned out there was a absorption because of the water, but now the newer fiber have come out where there is no water absorption. The other popular window here is this, the O band. This is 1300 nanometer. The attenuation is a little larger here, but the benefit is that the dispersion is 0. So you can transmit long distance, this is very, very useful. Now, another band here, initial systems, actually, this is gallium arsenide-based devices. Right now, this is the band here, the first window, where all the datacom, the data center, they use vertical cavity surface emitting lasers, they are used. So your new smartphone, they would be having a 3D image sensors in there that is based on an array of pixels, 32 by 32, thousands of pixels in there. That is vertical cavity surface emitting lasers. They belong here. They use 904 nanometer wavelength. Data centers, they use 850 nanometer. If you go a little further here, then all your CD player, your DVD player, then they use the wavelength 650 nanometer or 400 something nanometer. So the entire spectrum is really used. So when we're talking about lasers, they really belong everywhere. So you really need to know how the device works, how to make it. So by changing the material, changing you can change the wavelength. So this is here, the system here, the indium phosphide based, indium gallium arsenide phosphide, that dominates, right? And here is the gallium arsenide base. So this system is dominated by gallium arsenide, and this is by indium phosphide. Now, why do we need photonics? Well, it has really becoming a necessity today. So this chart here, this is the Maslow's hierarchy of needs is modified. The bottom layer was not there before. So if you do MBA or marketing course, any psychology course, so they begin with that. And your entire behavior, your family runs because of these needs, right? They are the needs. Needs decides our, state of mind. But now this need, the broadband connectivity, that has become the fundamental need. And we will talk about the other needs tomorrow, by the way. I have another talk tomorrow, so we will be using the same chart. But today, we are talking about the bottom. This has become the basic need. Even to get the basic need, your food, shelter, clothing, you need to work, you need a phone, right? You need a connectivity, right? But right now, we are at the beginning of the fourth industrial revolution. You must know that. That is this artificial intelligence. That's what the beginning. We had 3 industrial revolutions before the discovery of the steam engine, the steel, phone, mass production, light bulb, 1872, 1914. And then you have the ICs and personal computers and internet, digital age, 1970 and afterwards. But now we are beginning in the fourth industrial revolution, and this is the beginning of that. And they are the different technologies where you have the 4G, 5G wireless, broadband wireless, wired access network, big data, deep learning, machine learning, cloud, data center, fast processors. So these are the different technologies, and that leads to artificial intelligence, robotics, drones, virtual reality, augmented reality, autonomous vehicles, wearables. And that leads to your smart cities, smart villages, smart street, intersection, enterprises, smart living. And the core technology for all of that is the broadband connectivity. And for that, you need the optical link. So many of you may be doing physics, MSc. Do not think that this doesn't belong to you. You can always change. I changed my field so many times. I worked in government of India, for 5 years, and I felt that I was wasting my time. I changed it. I was working on materials and devices. I changed it to systems. So half of my lifetime, in United States was on materials and devices, and then the other half was on systems, So you can change it. Life is too long, So if you feel that you are not doing the right thing, you can change it. You can go and do masters in artificial intelligence. Many universities now are offering a master's course. Now you have to understand that the networks, how this connectivity, how I'm talking to you, you should know how does this system work, right? When you are teaching your students, they should get a bigger picture. This is how the system works. So I'm sitting here in New York here. So on the seabed, this is called optical fiber. This is called submarine system, undersea cable. So there are undersea fiber cable lying there, and they go there and they come somewhere in Bombay, and this is called undersea system. And from Bombay, it comes to Delhi. That is called long haul network, city to city. And from there, it must be coming to Hisar. That is, again, core network. And in Hisar, you have a metro network. And then from there, central office, so this is the metro network, and this ring here, and from here, a fiber comes here, and from there, this is called access network. It may go, next slide I'll show you. So this is access network. And here it can also go to an enterprise, like to a bank or to railways or to the government of India, or this is called enterprise network. So there are different networks. A military will have their own network, right? You have a sensor network, or you have free space optical network. So all these networks, right, their needs are different. They use different kind of wavelengths, different kind of lasers, different kind of detectors. The reaches are different. And when you design a system, it goes by layers. There are 7 layers, right? These top 5 layers are called software. And the bottom 2 are data link and physical layer. So we'll be talking about today only the bottom layer, physical layer, not the other layer. And Indians are really contributing a lot, wherever you go throughout the world in the software part. So India has a huge contribution here and the top 5 layers. So the access network, I told you that. So over here in this central office sits this box. This is called OLT, optical line termination, and from there goes the optical fiber. There are different versions of fiber to the home. I'm not going to go into details of this right now. So one fiber comes here, and it can go all the way to your home. That is fiber to the home, or it can go near the curb. That is called fiber to the curb, and there you can convert it, to the copper, twisted copper, the old line, and that is called DSL, ADSL, VDSL, different version of DSL. So many times you may be getting connectivity at your home through your twisted copper wire. I do not know in India, but there is called broadband cable, or you could have a cable called DC cap here, and you can bring coaxial cable, or you can have a hotspot, or it can be connected to the cell tower, and cell tower, you get connectivity. So that's how it works. So you see that this box here, so one port here, one port, it can support about 128 customers, right? It goes to a factor of 2 to the power 2 to the power 4, to the power 5, like that. So these ports here, they connect to the network here. So this is called broadband access network. And in the wireless, it could be fixed or mobile. So India has decided that every gram panchayat will be connected to the fiber to the home. So you see, you have a huge requirements in India, because if you connect to the gram panchayat, what do? You can create a lot of industry there, right? You could have your own eBay system in the village, selling the cattle, selling the crops, and the cities. So it will provide a lot of opportunities. The sad part is that India has only 1.3 million line, 13 lakhs line only, compared to in China, 350 lines, right? In India, Bharat Fiber or by BSNL or Geo Fiber, they are deploying this. But Indian cost is the highest in the world, $1,580, right? This is a shame, right? As opposed to $200 in China and $500 in USA. So when we say that the labor is cheap in India, this data doesn't show that. So you people have something to contribute here. So I mentioned that here in this diagram, that you have the link here, the transmitter receiver. But in between, you may like to have, if the distance is long, like in the undersea, right? The undersea, the distance here, it could be a few thousand kilometers, right? 6,000 kilometers between New York and London. So what do you do? So in between, earlier, there used to be regenerator. That every 50 kilometers, you have a regenerator. Means you get the signal, converted it, and then regenerate it, and then again transmit it. So this was the old system, right? And it was quite expensive because what data you need, power, you need a lot of things. But things changed in 90s, early 90s. That is the invention of optical amplifier. So you don't generate signal, you just amplify the optical signal itself. And this optical amplifier, this has really brought a revolution in communication. And right now in India, the lot of activities, a lot of people actually working in this fiber. You may fiber lasers or fiber amplifier, this all optical amplifier. And what it works is that you have optical fiber and you have a signal and you have a pump signal, that is also laser signal. You let them go through the fiber, they interact, and the signal get amplified. So most of the amplifier today, they are called erbium doped fiber amplifier, which is called EDFA, and the one you need for C-band and L-band, and for there you need a pump. Pump is normally 980 nanometer laser or 1480 nanometer laser. But new fiber amplifiers are being developed. That is thulium doped fiber amplifier for 1450 to 1490 nanometer range. Then another one for 1300 nanometer range. But most popular is the semiconductor optical amplifier, which is essentially a laser without any feedback in there. So you let the signal as well as you go through it and it gets amplified. It provides a gain medium. So this is very popular now, and it is at the transmitter side. So again, this is a PN junction. The most important thing is the Raman amplifier. So the Raman effect, there was no application or nothing. People did not know what is this. But today, when we are talking, our signal is going through Raman amplifier somewhere, because Raman amplifiers are very popular now. It can increase the span, by another 20 kilometer, 30 kilometer, which is huge benefit. And there are two kinds of Raman amplifiers. It could be a lumped element or it could be a distributed. Lumped means you have a standalone unit and inside you have fiber. Again, you need a source, a pump source, another laser, shorter wavelength, and you signal it goes there and power gets transferred from pump to the signal. In the distributed one, the transmission media itself, you send the signal, the pump signal, which can propagate along the signal or other direction of the signal, and the power gets transferred. So that is called Raman amplifier. And this is also, very popular today. Everywhere it is used. And without this, a lot of things will not be possible. So the amplifier, they increase the cost and the size, weight, power. And so people would like to see that they design their network so that they don't use the amplifier. But as I mentioned that all these fibers, optical amplifiers, they need a pump source, and the pump source is also a laser. So important thing that we must know how to make a laser and what are the different kind of lasers, different kind of materials. So that's what it is. Now, what is the universal requirement of industry and end users today? The universal requirement, you are a buyer, first requirement would be the cost, right? And the cost keeps going down, right? Electronics cost always keeps down. It goes only in one direction. In the case of electronics, TV you buy today, next year the cost would be lower. You would like to have more functionality at reduced size, weight, power, that is called swap. So even if you invent something which already exists, but if you can reduce the swap and cost, you are a winner. So you will see a lot of patents are filed today is because people are reducing the size, weight, power, and the cost. So think about a soldier, right? If you can, a soldier normally carries 50, 60 kilogram weight. If you can reduce the soldier's weight by 5, 10 kilogram by designing something, you are doing a great service. So other requirement today, I mean, is that you would like to have 24/7, you know, every day, 24 hours connectivity, right? I'm midnight from here, I'm able to talk to you, your morning. So anywhere, in any form, anytime, right? So this is called voice video data. So that's, and you like to have large bandwidth, very low latency. And that's why, you know, what we are doing today is voice or IP. And if there is a latency, then things would, then you will not be able to hear me properly. So the another trend is convergence. Convergence means this is voice video data. That's one example. But a single smart device like your smartphone, single operator, and all kind of apps there, which is like software. So your phone works like a calculator. It can alarm clock. It can work. Now your phone, think about that. How many radios it has? You know, at least it has 5 radios. You have 2G, 3G, 4G, 3 radio. You have GPS radio. You have Bluetooth radio. You have Wi-Fi radio, right? So you see that how many radios it has, and you do not even know about it. It doesn't ask you. It's transparent, right? The cost today, we are able to talk, is free, right? When I came to US, each minute used to cost me $3. And they used to count per minute basis, but the calls are free. Why? So if somebody asks what happened, we changed system from circuit switch to packet switching. So earlier, circuit switch, it was just, if I'm making a phone call, then all the network resources were allocated to you, and the call will go from point A to point B. But now we are sending packets, just like you are sending a letter in the mailbox, you know, in the post office. It will go there. But the speed is so large that the packets, they go from different routes and they come to you so at such a high speed that they get assembled, and you don't see any latency. You feel that signal is coming continuously, just like you are sitting in a theater and you are seeing a film. So you are seeing discrete, right? You have 50 frames, 30 frames per second, but it looks like continuous film. So same thing is happening here. We change from circuit switch to packet switching. We had digital platform, not the analog. Everything is digital. That's why voice, video, data, they all are bits. And quality of experience. You know, continued innovations with friendly human interfaces so that anybody who has no knowledge, no school education can use the device. So other trend is that design, development, manufacturing, and marketing across the globe. So even working in India, sitting in India, you can work for an American company or Chinese company, any company. You can do the design there, or you can do marketing there, and shorter product development and life cycle. So that's the important thing, and that's where India is losing. You know, time concept. So everything, you know, if you are late, it's no use. Other thing is that the trend is that software-defined system with network function virtualization. So you buy the trend is that you buy a white box, and you have your software, people write the software and work. So that's what GeoFiber is able to, you know, have the cost low because they are buying from Samsung, they are buying the white boxes, and they have the software people, and they write their own software code. They don't need to buy a license. So there are a lot of things here. They are to the benefit of India. So why should India develop its own devices? Why should you work on? Strategically important, right? It's necessary to ensure, you know, availability of the critical components, right? It's required. Defense requires this, right? Space program requires this. Our atomic energy program requires it, right? So we need increasing component requirements to reduce the cost, extend the state of the art, and develop the next generation devices. And have a technology as, you know, even if you don't do any of this, at least you will be an intelligent buyer. You will know what you are buying and can negotiate price better. Benefit is that India can produce, can consume, and export. The challenge for India is that there is a lack of funding, lack of R&D facility, non-manufacturable technology devices, transition to manufacturing. Even if you develop in the university, what do? You will take over, and hardly any industry. And you are the young people, you have to really address these issues. Now, this was my, the introduction. Why? Now I'm going to start with the technology part, right? So many things I'll be telling, they are elementary. But since you are, teachers or you are scholars, I put things together, for complete sake, so that you can. The complaint I hear every time, the students are not motivated, because many times we give the information piecemeal basis and they do not know why they are doing and what they are doing. So we have the metal semiconductor insulators, right? And important thing that any device needs all three. Many devices fail because you don't have good ohmic contact. If contact resistance is larger, then you will have heat dissipation there. The temperature of the device will go and device will die. So the lot of devices fail because the contact resistance is not is outside the acceptable limit. The insulator is extremely important. Most of the devices again fail because they are not insulated. It's just like you go in the winter outside without clothes. So the insulator, so the metals and insulators, they are as important as the semiconductor. And how do they work, right? So so you have the conduction band, the valence band, and this band gap, right? If it's large, then electrons can't go valence band to conduction band. This is insulator, and this is semiconductor. If you add impurities, it can change the conductivity. And in the metal, there is overlapping here. So these are different things here, right? So the band gap changes with temperature, pressure, stress, electric field, light, doping, size. So these are the properties actually we use, to make different sensors, to control different properties. So if you want to measure the pressure, or you want to measure stress, or measure electric field, or you want to do modulation. So some of these properties we use that, right? And if you know the band gap and in electron volt, you can convert into the wavelength, that is cutoff wavelength, right? So for any semiconductor device, all three are needed. All three. If you don't have a lot of product fail, I said that because you don't have either good passivation or good metal contact. Silicon is blessed because they have native silicon dioxide. It's very solid oxide. 3,5 semiconductor do not have that. So over here, group 4, germanium silicon. These are the group 4 semiconductors. So most of the devices are in silicon. Our oceans, they are full of sand, full of silicon, very cheap. And 12-inch wafers are available today. Initially, the first devices were made in germanium. But today, what we are going to talk about is 3,5, right? 3,5 gallium arsenide, indium phosphide based system. So these are the materials. And why is that? It is because, first of all, the right band gap, because we need to get the right band gap. But the important thing is that direct band gap, indirect band gap semiconductors. In the direct band semiconductor, if you see the momentum and energy diagram here, and the conduction band, valence band. So when you have any transition, your both energy and momentum, they both need to be conserved. It's not only the energy, but momentum as well, right? So here, if there is a transition, see, this is the gamma valley, and this is, so here when electron goes from conduction band to the valence band or the other way, so both the momentum and the energy, they can be conserved by emission or absorption of a photon. This is the indirect band gap, because here the minima of the conduction band is not at the same K value as the conduction band's maximum value. So if you have to have a transition from here to here, in addition to the photon, you need a phonon. So here it is a 3-particle event, right? Electron, hole, and a photon. This becomes a 4-particle event. Phonon, photon, electron, and hole. So, and it's very inefficient. So your silicon and germanium, they are indirect band gap semiconductors. So silicon, you can't make any laser. But there are a lot of people there. They can go and fool the funding authority. Oh, I'm going to make a silicon laser. I will going to do this. And that's all bullshit. They all tell. You can't really make any laser in silicon. You can do optically pumped device that you put 1 watt power in there and can 1 microwatt power output there, right? The germanium is blessed. In germanium has that, this is called, this is L valley and this is gamma valley. So this is indirect band gap and this is direct gap. So in germanium, the direct gap is 0.6 electron volt, and indirect band gap, and the direct is 0.8. So you can make germanium detectors, right? And in germanium detectors, what happened that you can excite electron from to here, and that's why people are using germanium detector in communication also. The difficulty is that dark current is decided by this L band here. So dark current is pretty high, and absorption decided by this. So this is what happens, right? So it's very important that now here in the direct band gap, so you can use either indium phosphide based indium gallium arsenide phosphide system or gallium arsenide L gas system, right? So these are the two material systems which are in communication are used greatly. And here is silicon germanium. So now the next point comes homojunction and heterojunction. So the homojunction is a junction between the differently doped regions of the same material. In silicon you can have all the NMOS, MOS, CMOS, silicon PV panels, all that, right? And the devices are made using diffusion, ion implantation, epitaxial growth. In the heterojunction is the junction between two different materials of different band gap, and they should have ideally same lattice constant. If there is no lattice constant, then you have lattice mismatch, and that causes that dislocation and defects, right? And that's a big problem. So if you have the lattice constant here and band gap here, so you see that here, zinc selenide, aluminum arsenide, gallium arsenide, the size of the aluminum atom, gallium atom is about the same. So the entire combination, this is called compound. Gallium arsenide is a compound, but when you have more than two, this becomes an alloy. So gallium arsenide, aluminum arsenide, and gallium aluminum arsenide is an alloy. So the entire composition is lattice matched to gallium arsenide, and germanium lattice constant is also the same. So the first heterojunction bipolar transistors were really made in gallium arsenide and germanium because in 70s, because the same lattice constant. So germanium, zinc selenide also is the same. Plus the indium phosphide and indium arsenide. So here indium gallium arsenide phosphide, a wide range, given by this formula is lattice matched to indium phosphide, and that is what's used for communication lasers and detectors, right? So these are I told you that you need to have lattice match, and but there is something called pseudomorphic. If layer is very thin, then you can have a strained quantum well strained layer, but the layer is so thin, then the layer will not relax and create defects. You can still keep growing. So this is very popular pseudomorphic stuff, in HAMT and strained quantum well lasers. And so anyway, this is homojunction, heterojunction. Now the benefits of 3,5 compounds and alloys, is because electron mobility is very high, and the electronic saturation velocity is also high. This is very important. Mobility itself is not, that important. Saturation velocity, like in FET, electron travel at saturated velocity. And the band gap engineering, right? You can change the band gap. You can have gridded band gap. You have heterojunction. A lot of freedom you get, right? And you can make quantum wells, quantum dots, super lattices, and you can, in electronics, you make HAMs or HBTs. And silicon germanium, you put silicon germanium based HBTs, that is heterojunction bipolar transistor, use silicon germanium base. That is pseudomorphics. There is some stress there, but it's fine. And you can pick up the right band gap, whatever you want. And so this is the benefit here. And you see that here is the absorption coefficient for detector is very important, that you have as large as absorption coefficient. So for communication detectors, you use indium gallium arsenide, that is 53% indium, 47% gallium, and is lattice matched to indium phosphide. And it has pretty good absorption. Germanium also had good absorption, but the point is that it's because its direct band gap is 0.8 electron volt. So if you have any signal less than 0.8 electron volt, then absorption goes down. Certain things sometimes we ignore. When we have high-speed detector, so you have to have the junction capacitance as low as possible. Something people don't talk about it, that the dielectric constant of germanium is 16, whereas of indium gallium arsenide is 12. So the same thing, you make a detector in germanium or in indium gallium arsenide. So to get the same speed, same junction capacitance, you have to reduce the weight area of the germanium detector, right? Because the dielectric constant is larger. 16 as opposed to 12. And when it becomes small, then the window for the light to go in, that also goes down. Or you have to use an expansive lens, a spherical lens too. So sometimes, there are a lot of bullshitting goes on. People go, oh, we can make germanium detector on silicon very cheap. But when you package it, then you find that you are not able to couple all the light into the detector, or you have to use an expansive aspherical lens as opposed to a spherical ball lens. So this is something is important, the transport, how does the device work, right? There are different kind of transport mechanisms in semiconductors. So one is the drift, the current due to an applied electric field, right? You all know that, right? The current goes there as proportional to your mobility times electric field. And that's what your detector uses the drift. In the reverse bias device, you apply electric field, a large field there, and you generate electron hole, and they drift with the applied electric field. The FETs, they work under drift. Second one is the diffusion. The laser work on diffusion basis. The current is due to carrier concentration gradient. Concentration on one side is lower than the other side, and you are forward biasing the junction. So carriers go from one side to another. And that's what you use in lasers, in bipolar transistors. In bipolar transistors, you can create also a drift field in addition to a diffusion in the base, right? The ballistic transport. So you can combine both drift and diffusion in a bipolar transistor. Thermionic emission, that's used in Schottky diode in MOSFETs. The tunneling is an unwanted effect, but unless you are making a tunnel diode, that is a negative resistance diode. In old days, making a microwave amplifier used to use that. Surface recombination, that is the killing problem, because you have unwanted parasitic effect. On the surface, you have a lot of damping bonds, and the lot of device die because it's not properly passivated. So the surface recombination is itself is a field, and you have unipolar device, like you have single type device, FETs, or bipolar devices, lasers and detectors, they both are bipolar devices. The last 2 points are important here, thermal equilibrium and steady state. As a student, I used to get confused between them, because everywhere you go, system under thermal equilibrium, you have the boundary conditions. So I think it would help that you explain to students, that thermal equilibrium and steady state, there are two different things. In thermal equilibrium, you would like to see no net flow exchange of energy with surroundings, right? So whatever you are putting in, you are getting it out. Because if that doesn't happen, then you may find that the device will become hot or it will die. So the lasers, when you are operating it, you would like to see the device in thermal equilibrium. If not thermal equilibrium, then its temperature will go up, or it will temperature will go down, depending on how you're operating. So the device will die. So to keep that, actually, when you are operating a laser and you want to keep the wavelength constant, we use a thermoelectric cooler, a small device, costs a few dollars. You put under the laser chip, and you maintain the temperature like 25 degrees C or 30 degrees C, so that the wavelength remain locked. So for the lasers, you have the electrical pump energy, which is the current, and comes out light and heat, and this heat has to be removed. Steady state, when state variables are constant, do not vary with time. And it's important when you are operating a laser or detector, you don't want to see property change with time. You like to see that the current, that the power coming out of the laser is same, it does not change, or the detector performance does not change. So device should be under thermal equilibrium and under a steady state. So this is the transport based stuff. Now, any question up to this point from anyone? So that yeah, I'm going to the next part. Any question from anyone? Okay, so when you make a device, so the two important processes called diffusion and ion implantation. So in old days, you used to use diffusion and ion implantation. In the diffusion, what happened that you have any device, you put a mask, which is like a silicon dioxide, silicon nitride, or and open a window in there, and you can do the diffusion, put some, and you can diffuse the impurities. In the case of 3,5, the problem with 3,5 is that it is the fifth group element, arsenic or phosphorus, or antimony. They are very volatile. They are very volatile. So what happens that the wafer could get decomposed. So you have to, when you are doing diffusion, you have to use closed tube diffusion. So you put a substrate here, it's a graphite box here, and you put some sort of a diffusion source, and you heat it up, and the impurities will go there. This is how the diffusion will take place, or like this, a closed tube. You put your wafer here and put the diffusion source, and the impurities will go and diffuse there, right? So all the detectors, they are made that way because the impurities, if you put the impurities during epitaxial growth, then they diffuse. So you want to have very controlled diffusion to keep the capacitance as low as possible. So you diffuse the impurities. That's one way. Second one is the ion implantation. In the ion implantation, you take the surface and you bombard the surface with a high energy atoms, and they go inside, and then you do the thermal annealing, and in the thermal annealing, the atoms, they found the right place in the lattice. So this is how earlier, when you were making the MOSFET devices, they were used there. Sometimes you want to damage, you want to limit the flow of current, like vertical cavity surface emitting lasers. You would like to, in any laser, you need to confine the current to the right area. So and so you would like to see that outside the current goes only through the area where you want it to. Otherwise, the actual current would be much larger. So you want to reduce the threshold current and operating current. For that, you want to limit the current only, where you want it to. Just like a river is coming there, and many times you feel that water is going everywhere, so you will confine the river to a tunnel. So that's what it is. So they would like to bombard the lattice with some devices like oxygen or something, so that you create the passivation inside. So diffusion ion implantation, there are two important processes used. The old technique, first technique, actually I did my PhD, this is my boat there, I used in Sheffield when I did my PhD, liquid phase epitaxy. I designed this furnace and this boat, and in this boat, it was indium phosphide. That was the only technique you can grow epitaxial layer, at the time. There was no MBE, MOCVD at the time. So this is a unit there, and this is a slider, and these are the caps there, because group 5 element is very volatile. So you put your substrate here, and you slide it, and you actually bring in this slider on top of the substrate. You use a solution in indium based or gallium based, group 3 rate solution. Put some indium phosphide in there, or in indium phosphide or gallium arsenide, whatever you want to grow. You bring it over it, and then you cool it slowly. So you precipitate the epitaxial layer over it. So this was the technique, and it was used to give the highest purity material, highest optically bright material used to be by LPE. The problem was that this was not a manufacturable technology, because the wafer size here at the time was only like 1 centimeter by 1 centimeter, or maximum, 1 inch by 1 inch. Somebody has a bigger system. The temperature uniformity was bad, and what was there that it was not scalable. So people were looking for new technologies, despite the fact that it was growing the best quality material. Plus the growth rate is pretty high, few micron, per minute. So you can't grow the quantum well here. So, but this is what the liquid phase epitaxy. You still used it for making the isolators, So the technique is if somebody wants to do in India, so this technique, you don't have to buy $1 million equipment. You can build it your own furnace and can grow the material if you want to really do some experiment. The thing is that the thing was replaced by this at the time was the molecular beam epitaxy. And in the molecular, this is a very sophisticated equipment. It's a vacuum system, and it's a cryo shroud where you cool it with the liquid nitrogen, and you add different cells, diffusion cells. You heat the material here, and you evaporate them, and substrate sits here, and you rotate substrate for uniformity. You have a shutter here, so when you remove the shutter, you start depositing. It's a very ultra high vacuum. The base pressure is 10 to minus 11 torr, or even better. And you can also see the oscillation, the gun here, and you have a screen here. You have the ionization gauge. So anyway, this was the MBA system. And but the thing is that very high, it costs like $1 million. And operating also, because you need liquid nitrogen and you need, everything has to be right here. And this is when I was hired in Bell Labs. This is what I did for 10 years, So this is my MBA system. I had only one machine, but I did extremely well. I grew the highest purity gallium arsenide here. So my management was happy. They allowed me to buy another machine. So I connected 2 machines together here. So there are 2 machines here. And actually the laminar flow hood. So this machine go inside the laminar flow hood, so that I used to load, unload inside the hood. And you see this white pipe here is coming the liquid nitrogen. Outside used to have a big tank. So liquid nitrogen coming in, cooling it here, and this is the transfer road. So this is the thing that I did here, develop the pump lasers, 90 nanometer pump lasers, end-to-end process here. I also developed here first non-hermetic lasers here by developing a special facet coating technology. So this is the MBE system. But the technology which is used, this technique here, MBE, is good for gallium arsenide based. If you want to use phosphorus based, the phosphorus pressure is so high. So you need to a turbo pump, and is a lot of issues. The people are using it, now, but it's not a desirable technology. For phosphorus-based system is more MOCVD. In MOCVD is use gases here. You don't use the solid sources. You use the gases, and you use hydrogen gas as a carrier, and you use different sources here, and you heat them up, and the vapor go there, and they go with the gases, arsine or phosphine, depending on these are the dopants. If you are depositing N-type, hydrogen sulfide, or use zinc for group 3, for p-type impurities, and they go inside the different walls here, and you have a substrate here at a heated temperature, and you deposit, So over here, this is a vacuum. This you are depositing the matter, and inside, at high temperature, the atom will move around, and you will have epitaxial growth, and you can control atom by atom. You can have quantum dot, quantum quantum valves. You can grow, just single monolayer by this technique, right? So here, vacuum deposition here is the reaction on the surface, right? It is not the deposition. You are bringing the different gases, and they mix, and on the wafer, then you have the reaction between them, and these are ultra pure sources, and they're injected to the reactor, and finally close a very thin layer of atoms on a heated and rotated substrate. So the pressure here is not that high. It could be 10 to 762, but you are using toxic gases, phosphine, arsine, liquid trimethyl. They are very toxic gases, right? And so extreme care is needed here. So what is the choice between LP and MBE? That depend really on application, So if you are using gallium arsenide based system, then MBE is better. If you are using the indium phosphide based system, then MOCVD is preferred. Anyway, there are a number of benefits for each technology, and when you want to do something, unless technically necessary, MOCVD is the preferred technology for manufacturing. Once you grow a material, it has to be characterized. So many times you spend several months or a year just to qualify the reactor, right? And it's extremely important, So it takes a year or more to commission and qualify a reactor, You qualified the source material, your growth temperature, gas pressure, flow rate, etc., the uniformity, the surface morphology, growth rate, doping concentration, alloy composition. You use the different technique with your X-ray, or you use the SIMS, or you use photoluminescence, electrical, optical properties, the reproducibility. All these parameters you have to characterize, right? And you use optical microscope, electron microscope, the whole measurement, CV profiling, photoluminescence, electroluminescence, X-ray. So in Vijay Jinyani in Jaipur, Malviya Engineering College, he has all the technology, it's fully equipped here. If you want to, you can make lasers, especially Fabry Pro lasers. Very simple, you can make within a day or two. You make LI, light and current, IV characteristic, threshold current, slope efficiency, wavelength, power. So that's how material is characterized. So now this is about the laser. So the laser is, I just took an example here that is principally is very simple, that you have a substrate, a highly doped and doped substrate, right? Because you want to have low resistance, right? Series resistance. So substrate is quite thick, so you use always N plus substrate. You grow first layer, that is N-doped layer, because N-doped substrate, and then you grow active layer where the action take place, and P-doped layer, and put the electrode there. So for FabriPro, you can just grow a layer and you can go to your clean room, semi-clean room, you can make a device, and next day you can have a results, right? So today, most of the lasers, actually all the lasers, they are quantum well, because in quantum well, you have very low threshold current, high efficiency, and essentially, I mean, I just showed here for simplicity, but that's how it looks like. You have a cladding layer. The top layer is called cladding layer. You have to confine the signal, the electrical confinement, optical confinement. So electrical confinement means you are injecting electrons from one side and holes from the other side, and they should remain confined inside this region. And then optical confinement, the light which you are generating, it should not go out. So for that, so this is called the confinement region here, and this is the quantum well. So action takes place here, where the electrons are injected from the N side and the holes are injected from the P side, and they recombine, and you get the photons out of it. So this is I showed here a single quantum well, but if you want to get more power, you can have 2 quantum wells, 3, 4, 5. In indium phosphide, people normally use 7 or 8 quantum wells. In gallium arsenide, single quantum well is good enough. 2 quantum wells, good enough. So because in the case of gallium arsenide, the confinement is better. The refractive index difference between gallium arsenide and aluminum gallium arsenide is much larger than compared to indium phosphide, indium gallium arsenide phosphide. So now you cleave it. The good thing about 3.5 is that the cleaved facet is 1, 1O. It is perfectly perpendicular to 1, 0, 0. So when you cleave it on both sides, you have perfect mirrors. That case does not exist in silicon. Silicon cleaves on one plane, but this here it cleaves on 1, 0 plane. So you have you get more power. You do the coating on the facet, HR coating, AR coating. But even if you don't do any coating, you will have the cavity, because the 30% reflection on both sides, and you have this cavity, and you will see the light output, and you can see this. So this is how you can make a FabriPro laser within 2-3 days. But these FabriPro lasers are very cheap. You can grow on 4-inch wafer, 50,000 devices. You can make it single growth, and the yield is really pretty good, because it's very simple devices. So for the low-end application, we are using like local area network. You are building system like in your just a building or in datacom. That's what they use FabriPro, because they are very easy and very inexpensive. But when you have the communication stuff, right, starting from fiber to the home, all the layers are DIB lasers, where you have the gratings. Gratings is a periodic, layers here, and it provides the distributed reflections. So here the laser action is not depend on the reflection from the facets. It's based on this distributed feedback from this grating. And there also, we have multiple types. You can have the gain media here, and you have the grating here. So this provides the reflection. This is called DBR. And what happens that you can change the property of this by putting a heater on this. So you can change the refractive index so you can make a tunable laser by changing the index and reflectivity. So this where you get pure spectrum here, DBR, all the tunable lasers are based on DBR, or you can have DFB. In DFB, you have 2 modes there, but you put AR and HR, then you can suppress one mode and we get one mode, but you will 50% yield here. And but then you have phase shift distributed feedback, where you put a lambda by for phase shift here. You also get very clean signal here. but then you have put AR coating on both sides and you use 50% power because you are taking only one side power. So here, when you make DFB lasers, it requires minimum 2 growth. So you first take the base epi, and I'll show you next slide. Now this is called edge emitting lasers. Then the second type is vertical cavity surface emitting lasers. In the vertical cavity surface emitting lasers, you have the bottom mirror, top layer mirror, and in the gallium arsenide, you can use gallium arsenide, aluminum arsenide. Refractive index difference between the two is pretty large. So you have the quarter wave stacks, 15 pair, 20 pair, depending, what kind of device you want to make. So you make gas, L-gas, gas, L-gas, gas, and aluminum arsenide on bottom and top. And this is your gain media. And then I told you before, ion implantation. Through ion implantation or through selective oxidation laterally, you create a passivating layer. So you see, when you grow it, it was gallium arsenide, aluminum arsenide stacks, but then you passivated it by either bombarding, doing ion implantation, or through some way, selective oxidation, you create an insulating layer so the light comes out from this here and you do the contact here. So this is vertical cavity surface emitting lasers, and this is what now is used in your 3D imaging, the LiDAR in datacom. So VCSELs are, is a huge in a huge demand. I have worked on all these devices and I made them the first VCSEL arrays we made in Bell Labs here. And so you see that's how it looks like. It requires at least 3 growths. So here, 2 growths, base epi, and then the grating and another growth. So how does this work? You take the wafer and on the wafer, you grow the base epi. That is the bottom cladding layer, that is N+ layer. And then wafer comes and then you make the grating. There are 2 methods of grating. You use the holography or you use electron beam lithography. Benefit of electron lithography is that you can have multiple wavelengths on the same wafer, and by the grating you can decide, you can write whatever you want to write. So you can have the gain media can support few nanometer, so you can have multiple wavelengths. In the holography, you cannot have that. You have the same. So you can use holography or grating. Plus holography is also good for 2-inch wafer. If you want to go more than 2-inch wafer, then you need a very powerful laser for that. So right now for 2-inch wafer, 2-inch wafer is that's what people are using, but people are going for 4-inch wafer. So grating, e-beam lithography, then you have to regrow on that. And you can regrow on that one, the top layer, and then you form the ridges by dry etching, and then little chemical etching to remove the stop etch layer, any damaging. So you get ridges, and then you do the passivation. And passivation, you can use silicon nitride, silicon dioxide here, or you can also use another growth, and that the top layer growth for planarization, that is called breed heterostructure layers. So for the low cost, people just use the ridge waveguide formation, and because what is happening now, people are using the foundries. So foundry, you just can't keep sending your wafer again and again. So the company I was working with, so you get the wafer, you do the base epi get them and send them to one company, will write the grating and then send back it to them. They will do the regrowth, and then you do the processing here. So if India wants to manufacture there, so I guess it would be very difficult for India to do this process here. You have to get this wafer from a foundry. There are a number of companies there, and you can do this processing here. So you do the passivation, and after that you do metallization. So earlier slide I told you the metallization and passivation are extremely important. Most of the lasers fail because we don't have proper metallization. Your resistance is high, and then you get the devices here. This is the wafer, and then you do the sky bars. So you see the dark region, each one is a laser. And so you do that here, cut the bars, and you stack the bar one over the other. In between, you can put a spacer, like a silicon bar, so that they remain separate. And then you stack them, and you do the coating. AR on one side, that is anti-reflection coating. essentially 1%, less than 1% reflection on one side, and HR coating. HR coating about 90% other side. So 10% will light come out, and on that, you put a detector. Detector will monitor the health of the laser. So when you have a packaged device, it should have the laser and a power monitor on the back side. So the HR light, we are not using it. We are using it for monitoring how the device works. And then you have to test the bar. Each device goes through automatic tester for different parameters, and the devices which are bad, it has all the devices are numbered, will tell you which device working, not working. And then there's a tick mark here, when you're doing cleaning, so you put tick mark and then you separate this device. So each tile here is a laser. And the dimension of that is 1/4 millimeter by 1/4 millimeter, 250 micron by 250 micron. And then it goes into in a package and you test. So this, you measure it for threshold current, operating currents, slope efficiency, power output, ARHR, wavelength, side mode suppression ratio, series resistance, and then you have to age the devices. So you see that here. You see that your network here, you won't be able to tolerate if the network fails, because a single device, single layer is sending you all the signal, maybe 1 terabit data, a single device. So you would like to make sure that every device is perfect. So first you do the burn-in test. So every device after it's gone there, you have to do the burn-in. Means you leave at some temperature, 100 degrees C, 120 degrees C for a number of periods, and they test the device again. And if there's a failure, if more than 10% variation has taken place, then you throw the device. And that's a useful life and wear life. So for this, you have to do extended aging process. You have to take multiple wafers and 3 devices from each area. So this itself, qualification processes may take you 6 months or 1 year, just like vaccine for the COVID-19 taking time. This also, so you can develop a laser, but it has to go into a system, communication system. It may take 1 year just to qualify the device here. And because the device could fail for a number of reasons, you may have defects inside, your facets are not clean, the wavelength may not be right, the contact may not be right, you can have the catastrophic optical damage, or bonding, when you have to bond the device, you have to have the wire bonding. If your pressure is not right, during the bonding process, you might create a crack or you might damage it. So because of that, your threshold may increase, your slope efficiency may increase, your power could reduce. And what happened that it becomes a positive feedback. If there is some defect there, you will absorb the light there, or temperature would go up, and then there will be further degradation. So you see the oxidation, facet melting, melt diffusion. So all these stuff, they help to kill the device. In the case of photodetector, I told you before, you grow a crystal, there are 2 types of photodetector, PIN diode, AP diode, APD. So PIN is simple device, you have N region and P region, and you have the absorption region, I region. And for the P region, you dope with diffuse zinc here. And you do the metallization contact here, and here is your insulator, silicon dioxide or something, so that means you limit the current going through the device only through this. This is undoped in gas, and it acts as an absorbing layer. So we absorb here, and you do the multiplication here in a phosphide. In indium phosphide is more sophisticated structure. You want to absorb layer in one region and multiply in the other region, but you use again diffusion. For making the device, you start an epi, you grow the entire structure, you make an HL mesa, and then you isolate the device, and you complete the die, put the N contact, P contact, and you test the device on the wafer and separate the device and do the bonding. So that's how device. And actually, we developed a process on 4-inch wafer, and this 40,000 devices per wafer. And again, it's very sophisticated. You have to see what kind of dark current you have, what kind of sensitivity you have, and do they change with temperature? And there are different material system, you use them, germanium, indium phosphide based APD, or there's a new material now, indium aluminum arsenide, One of the, when you have that APD, one of the factors is that one requirement is that ionization should begin only one type of carrier, either electron or hole. In the house, if two people, if they both have power, then system will not work, because it would be very inefficient. So only one person should have the power to decide, so only one boss, not multiple bosses. So similarly in the device, you should either electron should cause the multiplication. So that is called ionization, multiplication factor, the K. So the K need small k, means only one carrier should, and silicon is very good in that, but silicon doesn't have the right band gap and is indirect band gap. So you should have a small k and large multiplication factor. Anyway, then you will have the device of low noise, and turn out that the device here in the aluminum arsenide based device ABD, they have low k and large m, so performance is better. This again bandwidth product actually made the devices here. And this is what you do when you make a device. You do the bit error rate versus optical received power. So this is for 10 gigabit per second, and this is the best sensitivity for all the commercially available APD detectors. And every device worked on this way for, it has more than 40,000 devices. Now, few minutes left. I just want to tell you that there are a lot of bullshitting is going on. People would like to see, oh, we will make integrated photonics. In the name of integration, you can go and fool anybody. But the lasers and detectors I just discussed with you, they are totally different devices. One requires highly conductive substrate, other requires semi-insulating substrate. Their structures are different, the growth processes are different, the dopings are different. One is heavily doped, one is lightly doped. The fabrication process are different. One is forward bias, the other one is reverse bias. The current level is high, different. Lasers require very high injection, and photodetector requires almost no current. So in one case, carrier recombination, the other case, carrier generation, in one case, light out, other case, light in. So you can't really integrate detector and lasers together. So what people do is that they can have 4 lasers on the same chip, and they can use the grating I told you. By grating, you can write, you can have the different wavelength on the same wafer, because they are separated only by 100 gigahertz or 50 gigahertz. So you can have 4 wavelength, and you can make a multiplexer, here, and can do demultiplex, and you can have 4 receivers. So this is what people are doing, and this is what commercially available, that you can get 4 channels, so you can get a single device supporting 100 gigabit data. Okay, so other thing people talk about that, oh, we will do monolithic integration of electronic and photonic devices. Will reduce the cost. That's also total garbage, because you need to understand that electron is very skinny and photon is very fat. Electron, if you take say 1 electron volt electron, its wavelength is only 1.23 nanometer. Whereas if you have photon 1 electron volt, its wavelength is 1240 nanometer, 1,000 times larger. So any device you make, it should have, the dimension of that the transmission line more than that. So in case of electronics, you can keep scaling down, right? You can have 7 nanometer, 14 nanometer, 12 nanometer FETs, CMOS, but here it does not scale. Photonics does not scale, because if you want to get certain power output, you need to have certain volume. If you want to detect it, you need certain volume, because you can get, 1 electron hole can generate only 1 photon. So if you want to get certain number of photons out, you need to have certain number of electrons hole in there. So it does not scale. So the electronics and photonics, when you talk about integrated photonics, so this is a very misused word. And the only thing integration you could do is this, okay? But you cannot integrate them. Give you an example here, a company called Finisar, they put a company, and this is the integrated photonics. They have a tunable laser here and semiconductor optical amplifier, and a Mach-Zehnder interferometer, and they did monolithic integration of this. All these three devices, right? All these three devices. And there's a thermoelectric cooler sitting here, and you have the optical isolator here, because isolator light can only go out, cannot come this side because there could be some reflection. And here is the wavelength local, power monitoring, and you put a lens here and device comes out. Now I bought this device, I paid like $3,000 and it works great. It's for RF or fiber. But turned out that it's so expensive. Something you can buy for $10, who will pay for $3,000? And the yield is small because you have multiple devices. If one fails, the whole device fails. And then you have to program it. So they bought the company, but they figured it out that they can't sell it. So certain technologies, they are even technically feasible, technically successful, but economically they're failure. Because I mentioned before, the cost, low cost, low cost, low cost. So that's what dominates. So anyway, photonics devices which are suitable for India for manufacturing. So the low cost and mass production. The LEDs for lighting, for remote controls, for display, for education, other applications, and silicon photovoltaic for silicon photocells. Private industry will make only investment for their captive needs, right? If somebody is, deploying a solar system, few gigawatt solar system, then they will go for this. Otherwise, they will not go. So government of India and you people actually are the crew. You people have to tell them, like the farmers having their strike, you people, the scholars should go there and meet your MP and minister, hey, do something here. So even 100% foreign direct investment is necessary because India has nothing, right? We need high power semiconductor lasers for material processing and low cost manufacturing. This is because the lasers are now used in manufacturing, This is another application, the UV LEDs for food preservation, sanitization and non-line of sight short distance communication for war fighters. So this is another application emerging. And near and mid and long wavelength infrared sources for detectors and night vision and sensors, short wavelength detector for UV, X-ray and X-rays, and VCSELs I mentioned to you for 3D imaging and sensors, optical interconnects, vehicle communication and LiDAR. Silicon photonics for R&D, if you want to use silicon photonics, they're the only thing that you can do optical beam forming and high-speed communication, the healthcare, agri-photonics, terahertz photonics. So, and use commercial foundries wherever possible. So actually, we had this summit, Web Summit, and I proposed this thing that India should have a National Photonics Institute. There's an institute in Ireland. I worked with them. Gave them like $500,000 to get something done by them, and I suggested that that this should be there should be 1 or 2 centers in India, maybe co-located with the IISc Bangalore or this semiconductor lab in Mohali. May require like $100 million investment. There is a place in University of Pennsylvania here, one Indian, one Krishna Singh, he donated $20 million, and have a nano fabrication facility, and after name, Singh Nano Fabrication Facility at UPenn. So India could invite, some rich people, ask them, hey, set up this facility, name after you, and all that, So anyway, this is the proposal I made to them, and made quite a few recommendations. Now, this is my last slide here, but I'll spend 2-3 minutes because in these panels, almost everybody was complaining their problems, and they say they buy equipment, expensive equipment, and there's no money to get it repaired if it gets bad or they get damaged, they have to throw the equipment. So here are some recommendations. Many of you are faculty members or research scholars. So in the life, you need a balance. Should have a short-term projects and long-term projects. Like short-term need what country needs today, and the long-term. You can't just say that all research we do in long-term. You define the national priorities and note what we can do. And in the university, just for namesake, have an industrial advisory board comprising experts and operators. You just have a, maybe your alumni, your students. Have few students, bring them. Only for namesake that they are there. Learn what are their pain points. Like I'm talking to you, get some people in your board. And it's nothing, just formality. Have just officially that we are industry advisory board, and visit them, invite them, offer them help, and they will help you. Will you donation? Have an industry day. But collaboration and partnership is very important. You cannot have everything yourself. So whatever you do, you should be open and find partners so that you can work with them. If I do not have the partners, I do not have the mentors, I won't be able to do anything. And develop prototype and test beds where possible, right? For the smart cities, smart towns, you can think about that, right? So making components very hard, but getting components and building a system based on components is relatively easy and require almost no maintenance. So important thing is that develop the best practices in your lab. Recognize that the equipment and components are very delicate today, right? They can be easily damaged and may not be repairable. So read operating conditions before you use anything. The one thing which I found that in a number of labs in India, ESD, that is electrostatic damage. So if you are working in the lab, using high-speed equipment, it can seriously damage the equipment. So you should have ESD flooring, and you should ground yourself, discharge your RF cables. Many equipment, if you are using, they also have a requirement with the AC coupling, DC coupling, using the right connector. Some equipment have a sequence. How do you turn it on and turn it off? That you need to follow, otherwise you will kill the equipment, right? Don't exceed the power ratings. Use attenuator pads. Even if you are using an oscilloscope or spectrum analyzer, put always an attenuator. Passive components, they also have power ratings. Some capacitors, resistors may be rated only for 12 volt. But if you apply 20 volt, it will die. So passive components also have limitations. If you buy something, also get an evaluation board from the supplier. Always have good relationship with the application engineer of the company, the supplier company, and the marketing sales people. They're very, very important people. Today, if equipment is not working, you can use the remote diagnostic, can go on the phone and can see YouTube, and they can help you, have good tools in your lab, all types of nuts and bolts. Sometimes finding a right bolt, right nut, could be a project, and you may have to throw the equipment because you don't have the right screw. There are all kind of thread, different countries use different kind of thread, and turn the equipment off, when not in use, because it will not only consume power, but if there's a certain power failure, it might kill the equipment. So many labs I visited in India, people walk barefoot in the lab. And that's very dangerous. You can have a separate pair of shoes and, for the lab, but never walk barefoot. So with that, I will end, I would say that, I give this slogan, Jai Hind and Jai Photons, and that's all I have. And I'm sorry I've taken too much time, but we can have some discussions. Any question, we can address now.
Okay. Any questions, please? No. In the chat box, there are no questions. Any participant may ask. Okay. Thank you, Dr. Naresh, for giving a wonderful talk. Lasers and detectors. In the first section, you have very well described the opportunities and possibilities of this photonics field. And since I am teaching the course on fiber optics and semiconductor, whatever slides you are showing, I was enjoying those because these are overlap with my field. And the participants must have been enriched with the knowledge, whatever you have given. And your slogan, Jai Hind and Jai Photon, is very effective.
Well, that's important.
Yeah, this is very good. In fact, without photon, there is nothing. I always say sun is the only God which is visible to us. And we
we have a sun temple, sun temple in Odisha, right?
Yeah, Bhubaneswar.
And, Bhubaneswar, right? And, interesting that our C.V. Raman, and S.N. Bose, photonics actually in India started, much before than anywhere else, But I'm sorry, my talk was not advanced photonics as your topic is, but was more elementary stuff. But it was, I thought, people could get familiarized themselves, how things work,
Yes. Most of the terminology they have been given, they have been exposed with that, and now it is the young researchers to decide how to pick up the field of photonics. So photonics is a solution of every problem, even COVID-19. Yesterday, I was saying that the real-time detection of COVID-19 is also important, and photonics has a solution for this. So, I must appraise the participants that Dr. Naresh Chand is speaking from USA, and at this time it is midnight in USA, and he has
1 a.m.
Yeah, 1 a.m.
1 a.m.
So, yeah, 1 a.m. So he has taken all the pains to be with us, and thank you very much for agreeing to deliver the talk. And I would like to inform that tomorrow is also your talk, sir. Or it is
Yeah,
regarding spirituality. It is regarding spirituality and science
yeah,
and
that's it.
art and science of happiness and self empowerment. So that will be wonderful, and have a
So
wonderful
one thing I want to, the closing remark is
Yes.
that what I have discussed with you, I have worked on that.
Yeah,
And so it's not something that I'm telling you from the books. It's something that in my life, I worked on the different processes. And tomorrow also what I'll be discussing, talking to you is what I believe in, I practice, So I
yeah,
told
yeah,
you I come from a village where there was no paved road, where there was no toilet, there was no electricity, no running water, So if I can come from there, the way here, so you people have the potential to do anything you want, You are better placed. The one difference I want to tell you, the culture in India and here. So when I come here in Bell Laboratories, I went to my boss, to ask him that what do you think I should do? And he was very angry at me. He said, I hired you to tell me what company should do. If you are coming to ask me what you should do, then why should I hire you? If I had to tell, then I can hire a technician. So in India, I find that a lot of people are looking for their boss, Modi, to tell them what to do, or their boss, their advisor, or you really had to tell your advisor, you really had to tell your department head, you had to tell your principal, vice chancellor, what is needed and what needs to be done. So one thing I found that I was told, different mindset, right? That if you are complaining or you have something, you should go with a solution, a recommendation. If you don't have a solution or recommendation, all you are doing creating a noise. But if you tell that this is the problem we are having and this is the solution, then it will get accepted, So this is the point I want to tell you, that many times people say that how come people from India, when they go outside, they are very successful in India, the same people, highly talented people, but at the same time, things do not move. It is because we are waiting for somebody else. We have to empower ourselves. That's the point I wanted to make
yeah,
as my closing
yeah.
remark.
This is a very profound statement you have given, that we have to tell the boss that what to be done and how it can be done. So
Yeah,
that's
don't wait for them to tell you. At this time in India, it's paralyzed because everybody thinking that Modi knows solution for everything. Modi
yeah,
will do this.
yeah, yeah, yeah. This is irony
That's
of.
what came out of Bravo. Okay, Ji. Thank you
Anyway,
very much for inviting
thank
me.
you very much. Thank you very much, sir, for
Okay,
joining us. Thank you very
okay,
much.
bye bye.
I am extremely obliged. Okay, thank you. So,
Hello, Gagan ji.
Yeah, hi.
hi,
Hi.
hi. Dr. Gagan
I'm
Kumar
sorry,
has joined us.
it's
Yes.
1 a.m. I had to go to sleep, so sorry, I won't be able to attend your talk.
Yeah, it's
No
a very
problem.
good thing. Good to see you.
Okay,
Yeah.
bye bye.
Okay, bye
Yeah,
bye.
bye.
Yeah, we have with us Dr. Gagan Kumar from IIT Guwahati. So let me give brief description and citation for him. And here it comes. Oh, anyway, Dr. Gagan Kumar, he is from IIT Guwahati, and um, we interacted with him. He has collaborated with us, and he works in the field of terahertz. And I welcome him to this faculty development program, and he has very kindly agreed to give a talk during this event. And he's working very hard, I tell you. So remaining his talk will be his introduction. So I need not to say much words. He comes from IIT Guwahati and he belongs to Hisar. So earlier Dr. Naresh Chand was belonging to Ghaziabad. So the persons like small cities groomed up, and they have gone to various places and good places, and now are working in the field of photonics. So I just want to tell the participants that कुछ भी काम करने के लिए हमारे में जनून होना चाहिए. There should be fire in the belly. If we have the fire in the belly, then and then only we can achieve some goals. So, as Dr. Naresh was saying, that we have to tell the boss. Similarly, my statement is that we have to work for the organization. If we work for the organization, we are working for the society. We are working for our country. If we think of ourselves only, then it is not going to pay. So we have to think in a bigger way. So with these words, I invite Dr. Gagan Kumar to deliver his talk.
Yeah, thank you, Professor Devendra Mohan, and thanks all. And I really appreciate and thank you for inviting me to this FDP program. And it's really a pleasure for me to be the part of this program. So let me share my screen. And thanks for the kind words also. Let me share the screen, and I hope you would be able to see the slide of my presentation. Let me make it full screen. Okay. So do you see, are you able to see the computer screen, my laptop screen?
Yes, yes.
Okay, thank you, thank you. So I hope I can start. And thanks again to all the participants also for being here to this talk. Briefly you know about me. I'm Gagan Kumar, so here in IIT Guwahati. And I have been largely working in the area of terahertz and plasmonics. So in last couple of years, we have tried to club these two areas, terahertz and plasmonics, and how they can be clubbed together, and how the next generation devices, communication devices, can be made, can be constructed out of this concept. That is the motive of my talk today. And we have a laboratory called Terahertz Photonics and Plasmonics Laboratory, in which we are working. We do experiment, we do theory, we do simulation, and I'm also happy that we have a collaborator, Professor Mohan. So here is the introduction of my talk. So I will introduce, I have been told that the most of the participants are from MSc background, they are research scholars, and therefore I would like to introduce them very basic concepts of the terahertz, what the terahertz is, and what are its applications in different areas, how it can be useful in making next generation devices, whether it is sensors, communication, medical imaging, and there are many more applications like narcotic drug detection and all that. So I will briefly introduce about that also, and then along with that I would like to tell you that how the research in terahertz has grown in last couple of years. How people have been motivated to do research in this area because of many potential applications. And then I would like to also explain few of the sources and detectors. We have a variety of sources and detectors, although it won't be possible for me to discuss all, but I would like to discuss one of the very important source and detector called photoconductive antenna. That is more or less used in every lab. It's very simple as well as cost effective, I would say, technique for terahertz generation that can be done in our labs. And then how the terahertz waveguides can be built and why they are useful, in fact, how they can be building blocks for the next generation terahertz communication systems. So that will be my next discussion. And for making terahertz waveguides, we have been using the approach of terahertz plasmonics waveguides. Basically, the plasmonic approach we are using. And what the plasmonic is, how it can be used for making devices at terahertz frequencies. And we had made some devices in recent past, and currently also we have been working in this direction. So I would like to discuss how we have been making devices. I won't be discussing a research part in detail, but just to give you a flavor that what we have been working in the terahertz plasmonics, that I would like to introduce also here, and then followed by conclusions. And please feel free to, because this is a FDP program, and also if you have any questions, please feel free to interrupt me and ask me wherever you feel. So anyway, just very basic about the terahertz. Terahertz is a frequency, as we all know, and it has a frequency 10 to the power 12 hertz. Okay, just like gigahertz and megahertz, it's another frequency. And we have this entire spectrum, as you can see over here. And this entire spectrum, terahertz frequencies lies between the electronics and the photonics. Okay, on the one side we have the photonics components are being made out of this, at these frequencies, and on the left hand side we have the electronic devices. In between that, this narrow region has the advantage of both these regions, both the electronics and the photonics. That's why we feel that this narrow region, sometime back it used to be called as a terahertz gap. And in fact, I would say in terms of communication, we still call it a terahertz gap because we don't have devices. And they can take advantage of electronics as well as photonics, and the devices that we are operating currently at the speed of like gigahertz at the most, they can be made to work at terahertz or at terabits per second. We can make them to work. So since we don't have devices as such even today, so that's why we called it a terahertz gap, at least in the communication part. Okay, so our motive basically is to fill this gap, to come up with the components, devices such as filters, modulators, dichroic mirrors and all that in this region, so that we can build next generation communication system. So when I'm talking of terahertz, as I said, this is a frequency of 10 to the power 12, and on the time scale it corresponds to 1 picosecond, wave number 33 centimeter inverse, wavelength 0.3 or 300 micrometer. Okay, and they are very low energy waves. Okay, this is very important. In fact, if you calculate the photon energy at terahertz, then you would find that they are very low energy waves. Basically, their energy is so low that it won't cause any harm, unlike the X-rays and so. But they can do the things that the X-ray does. So that's why they become also important. In terms of the time domain, signal, every like sinusoidal wave, it has a certain profile. Similarly, we have a terahertz wave, and this is the single cycle terahertz wave, and it has a bipolar profile, as you can see over here. And if I convert into frequency domain, this will give you a broadband, spectrum. Okay, largely we are working with the broadband spectrum, but certainly if it is a multiple cycles are there, we will have a single and narrow band also. They have also different advantages and applications. So, but largely I will be discussing about the broadband basically system or broadband spectrometer that we use basically for building or checking the devices. All right. So let me give you the flavor of certain applications that it can lead to, or it has basically already in use. And there are many. One of them is the medical diagnostics. Okay, I already told you in the last slide that terahertz waves are pretty safe. One photon energy is 4.1 milli electron volt. X-rays have some hazardous, effect. They can cause cancer if they are not actually exposed. Human is not exposed in a controlled fashion. They can lead to several hazardous effects. And that way, terahertz imaging, if can be made, that would be, pretty safe as compared to the X-rays. In fact, people have tried to build such system. Like these are the two images if you see over here. This one, like, this is the imaging of the interior part of this teeth, this enamel. So here and dentine. So you can see that, this is a terahertz image and this is a visible image, and it very clearly distinguishes the interior portion and the outer portion. Okay, so the imaging can be done with the terahertz and in a very effective manner. Okay, and also early cancer detection. It has been found that cancerous cells, they have different absorption features at terahertz frequencies as compared to the normal tissues. So in that case, if we do the cancer detection at terahertz, that's quite possible. In fact, some research has been done in this direction. As you can see, this is one of the images that I have taken from TeraView. And they can, you see that these are the cancerous cells, and basically they did it with the terahertz imaging, and their absorption features, basically they accordingly recorded. The only some disadvantage is that it is absorbed by the water that cannot penetrate to a certain depth. So that's why this imaging is limited to the is limited to the basically at the skin level, or maybe just a few millimeter level. It cannot go inside the human body, but maybe some research is required in this area. Certainly some kind of endoscopy technique may be used or can be developed for the future, if you want to diagnose the interior portion of the human body, like the way we do with the fibers. Okay. And also same is with the tumor. They have different absorption fingerprints than the normal tissues. And also, as I already told you, this dental science also that can provide a clear contrast in the diagnosis of the interior and the outer portion of the teeth. So that way, medical science basically certainly would need, and in fact, a lot of work is being done in this direction, I would say, in terms of developing tomography technique based upon the terahertz. So those kind of researches are required at the terahertz, and they are also underway. Okay, and the main challenges I would say in this imaging technique has been to have the high power sources. Basically, normally the conversion efficiency is pretty low with the terahertz sources, and we get very low power. And this is one of the challenge I think that we need to address. So virus detection, we all know that we have been affected in the last 1 year by the we have been facing the challenge of COVID-19. So indeed, in that context, I thought of introducing this slide, and some research has been done in this area, and it has been found that basically terahertz waves can be also useful for detecting the virus, for sensing the virus. So this is one of the metamaterial unit, and some sort of a structure, artificial structure, I would say, when I'm saying metamaterial. And there is some gap, and in this gap, the structure is such that in this gap there is a huge field confined in this gap. Huge electric field concentrates over here, and whenever we have a virus hitting over here, then it will show some spectral feature. For example, if this metamaterial unit with this narrow gap is showing some resonance over here, and then if you place some sort of virus of certain refractive index, then the ambience of this narrow gap will change, and there will be a shift in the resonance frequency. Okay, and this shift will tell you the information about the virus. This is one of the research papers that were published in the past, but very recently some research also has been done about the COVID-19 detection using terahertz spectroscopy. There is a group in Israel which has basically found that terahertz spectrometer can lead to the detection of this coronavirus, and the accuracy is more than 90%. Okay, that's what they are claiming, and yet the commercialization is need to be done in this direction. But this is the recent update with the coronavirus related terahertz research. So this indicates also further that we need to further work in this direction to actually have more effective testing device that can operate at terahertz. As I said, that they are quite safe also. Let me go to the next part. Next part is the security screening application. In fact, terahertz imaging is one thing that I told you earlier, and security screening can be done for the passengers. In fact, outside India, at several places, at strategic places, I would say, they have these terahertz and millimeter wave detectors installed on the airports. Whenever a person, is there at the airport, like one in the Netherlands I have been through, they will make you stand in a chamber and they will expose you with the sub-millimeter or terahertz waves. And if a person is carrying some weapon, like a person over here, or maybe a knife inside the cloth or inside this paper, then it will detect. So what I mean to say is that terahertz is transparent to clothes, transparent to paper, wood, but it is not transparent to metal. So that's why a person standing over here, if he is having metallic items, so it can be without in fact manually going to the person and touching him, he can find out that whether he's carrying a weapon or not. Similar one image that you can see on the right hand side, there also a person might be carrying a knife inside, that is concealed in this footwear basically. And normally, something that is not checked with the machine, that the metal detector they have. But if simply you don't really need to go and ask him to remove the his footwear and all that, then they can just make you stand in a chamber where you will be entirely exposed to the terahertz. And if any metallic object, even if it is hidden inside the shoe, then it can be found. So this is very effective that way, and in fact this technique is being used also on the airports, and also it is very useful in security screening of letters. Okay, so sometimes we have the parcels coming to our home, and if a parcel, and it's very difficult for and we cannot certainly open those parcels, in the post office or wherever the couriers companies, they don't open it, they are not allowed to open it. Then how to detect if it is a weapon? So certainly they can do simply, they can place this parcel on a piece of this device, and basically it can do the terahertz imaging and find out like whether this is a gun or any metallic object is there. So this is another possibility that people can do the security screening. And in fact these security screening devices are in place in the in this terahertz research, or in fact being used at certain places. So another very important application that we have is the explosive and drug detection. Okay, terahertz radiations not only capable of providing images of the concealed weapons, as I told earlier in the last slide, but they do help us in identifying the elemental component of the hidden item. So I hope you understand this line, that we can see the image. Obviously, that is one of the advantages that we have the terahertz. Okay, imaging can be done just like the X-rays. Okay, but at the same time, what is the content? Whether he is carrying some explosive materials or some narcotics. Can we see that? Can we also know that? Means you can see the shape of the object, but at the same time you can also know what the material is. Okay, for example, if in a closed, if in an envelope or in some box, if what the person is carrying, okay, if it's a gun, then what you can find out. But if he is carrying RDX or any narcotic material, then that also can be detected. Why? Because terahertz, these explosives like RDX, TNT, and narcotics, they have spectral features. Their molecules, rotational and vibrational motions basically lie in the terahertz range. So means if it's a narcotic material or explosive, they can identify. This is certainly some spectral features by different materials, and as you can see that they have certain absorption features. So what we can do, for example, we can do the terahertz spectroscopy and find out where these absorption features are, and then we may have a database, and we can compare these spectral features with the database, and then if it is matching with the database, we can easily find out, okay, this envelope has this kind of material, and then proper action can be taken. So that's the technique. That's the beauty about this terahertz, is that you are also doing imaging just like X-ray, but X-ray only does the imaging, but here we can also know the information about the content also. That's the beauty. And also terahertz devices may be more promising, since they could sound an alarm if someone is trying to entering a subway or train station, has the traces of a bomb or something like that. So what I mean to say is that we certainly cannot detect each and every person, if he's going through a subway or through a common place, public place. What we can do, we may have our terahertz devices installed at those places, and whenever a person is carrying some sort of material, this explosive material that is used in making the bombs, then you know these devices will sound an alarm. Okay, then person who is sitting in the control room that can hear that, okay, someone who has just passed from here and he's carrying explosive weapons, and then accordingly we can sensitize that entire area and also action can be taken. So if we can have certain these kind of devices, then definitely, you know, we can you know, have a more controlled and security point of view approach. But why it's not there? If the only challenge that we have is that we need to have really strong terahertz devices, okay, strong terahertz sources, and already the research is underway in this direction. All right. So this is another image. I think this is another slide. Basically, this another image also here about the prevention of the criminal offense. Okay, this is one of the beautiful images that I could grab from somewhere. It shows that a person is there inside this chamber, and this wall is basically made of wooden. Normally outside India, it's like that, as you know. Sometimes, you know, these walls, the soft partitions are made. And we know that, you know, these soft partitions allow the terahertz to pass through it. And a person outside over here, he is having a terahertz gun. So what he can do, or the security person can do, that he can see through this wall and he can see that who is this guy is being kidnapped, or who is this, you know, kidnapper. And then he can accordingly basically make the judgment, okay? And then he can basically, this can be used for the prevention of the criminal offense also. And if we can develop this kind of gun, that certainly, again, as I said, that we do need strong terahertz sources and also efficient detectors. This is the key, you know, in getting this kind of technology. And if we are able to make this kind of gun, certainly this would be one of the biggest technological breakthroughs in the next century. Okay, so another application, that is the food inspection. Okay, food inspection is another very important property that we have in for the terahertz. So this is used also. Quality control of the food products. I already told you that if we have metallic content, metallic contamination, or metallic object anywhere, you know, even inside the clothes or anywhere, that will reflect back the terahertz. Basically, we have this will reflect back the terahertz, because metals do reflect strongly the terahertz. Okay, and therefore, if any metallic particle, metallic contamination is there, for example, this is the chocolate image, and outside, you know, it looks very nice, but if we have a metallic component, metallic contamination somewhere in this, somewhere you know, hidden, and that is not seen from outside. But if we just, you know, place it inside this terahertz source and detector spectrometer, it will easily tell, you know, as you can see over here, you know, it will easily tell here we have a glass, stone, or any metallic contamination. So that way also we can easily identify. And if this has to be done on a bigger scale, a bulk scale, you know, you can easily just place your, keep on placing your these kind of chocolates on any eatable material inside the spectrometer, and imaging can be performed, and you can find out the metallic or, you know, any contamination. For non-metallic contaminations, we can perform terahertz spectroscopy, but, you know, we may need some kind of, you know, algorithms, you know, for the distinction between the desired and undesired ingredients, but that's possible, you know. But that can be done also, and this research has been done, although it's not one of the research areas, but certainly, you know, a lot of work has been done in this direction. This is very useful technique. This is another image where you see that, you know, there is a ring there, metallic ring there, and you know, if you do the terahertz imaging, it will show you that something is there inside this eatable material. So that is very useful technique, and also food inspection is one of the very important area where which can benefit from the terahertz imaging. All right. Then we have communication. Okay, I will also speak about the communication in my slides. And we have seen that, in every decade, technological developments have taken place, 1980s to 1990s, 2000, and we have seen development, in terms of the first generation, 2G, 3G, 4G, 5G, we are, trying to get in very soon. And then certainly we would need 6G, okay? And 5G also promises until, I think, 100 gigahertz, okay? And that's what we are targeting, and soon I think it will become a reality. But at a point in 2030 or so, we certainly meet the demand of the data transfer because of the increasing population, or several devices, artificial intelligence, and all that. If we want to address those demands, certainly we have to come up with the 6G, and 6G will be operating at more than 100 gigahertz. What I mean to say is that the data will be transferred at terabits per second. Okay. Nowadays we have Mbps or maybe Gbps speed, as you all know. But what is the meaning that if we are able to transfer data at terabits per second? The meaning is that if we are able to do it, then means we will be faster as compared to Gbps, 1,000 times faster. Okay. So means, a movie that we are downloading in in 1 hour, and if we increase the speed by 1,000 times fast, if we increase the speed by 1,000 times, then definitely, it will be downloaded in a couple of seconds. Okay. So this is what we are targeting 2030s, and a lot of approaches are being used. In fact, nowadays, a lot of waveguides, a lot of modulator devices, are being researched. Research is underway in this direction for the development of such devices, and different approaches like plasmonic approach that I will discuss in today's slides. And also some topological techniques are also being used. So, but anyway, we have to, as I said, that in order to develop the terahertz devices, if we are going to have this communication that will be much faster, then we certainly need devices, right? And terahertz devices. And if we want to have terahertz devices, and then certainly we have to have the terahertz waveguides also. So I will anyway discuss in my coming slides about that, but this is one of the challenge, and I think a lot of research is required in this area. Okay. So anyway, before I come to the more technical part, let me just introduce in last couple of years how the research in terahertz has grown in last 2 decades, I would say. Just let me get the water. All right. So as you can see here, in 2000, when we used to have only about 200 publications, we used to see in Web of Science, and now if you see nowadays, until 2018, we used to see more than 3,000 publications every year, basically. Okay, and this is different data from IEEE journals. And also you can see there is a significant increase in number of publications that are related to terahertz. Okay, so this in itself tells you that how research in this area is growing in last couple of years in a significant manner. And whenever there is a research, certainly ultimate goal is to get the devices and also commercialization, especially when we are working with the technology. So, and money also becomes, important. So and this is the data that shows that, in 2012, when we had a market of like 280 crore, okay, and now this market every year has been growing, and by 2022, the overall market, terahertz market would be of like 2,800 crores, okay, and it is seeing this compound annual growth of 26% every year, okay. So, and as I already told you that we have a variety of areas in the terahertz, where terahertz can be useful. So I am trying to show here through a tree. I would say terahertz technology is a tree, and it has applications in almost every area. like material science, biology, laser technology, nano and micro technology, semiconductor technology, plasmonics. There are 4 areas that I have been working at the moment, and my students have been working basically in these areas. And these areas are basically Terahertz pump probe spectroscopy and ultra-fast carrier dynamics. Because this area requires very sophisticated laser system, and in recent times we haven't been able to work much, but yes, we have worked in this area. And also silicon, as you know, that is present in the nature in abundant amount. So therefore, can we use silicon for making Terahertz devices, just like the silicon technology? So that is another goal. In recent times, I have worked with silicon-based Terahertz waveguides. And then these are the 2 areas where we have been actively working in past 5-7 years. They are the thin film terahertz sensors, guided wave devices, high-speed communication devices, and also in metamaterials. I won't present the metamaterial part today. Maybe if I get a chance sometime later, then I would also like to speak about the metamaterials. And metamaterials we have been using, just like the split ring resonators, for making Terahertz photonic devices, switches, and modulators. But today I will introduce only about this plasmonics approach that we are using for making some kind of waveguide devices. Now let me come to different kind of sources and detectors. All right. So Terahertz sources. There are a variety of sources. This is just a flavor. I'm not going through again the very details. I will just discuss this one technique in my coming slides. It's not possible for me to describe in detail each and every method of Terahertz generation because this requires a lengthy discussion. In this short time, it won't be possible, but at least one technique I would like to discuss in detail. So this is very important technique, photoconductive antenna. And the beauty about this technique is that you don't really need a very high power laser system. You certainly do need femtosecond pulses because you have a bandwidth in that. But at least, even, if you have a 50 milliwatt laser, that is good enough for, even I would say 20 milliwatt power is good enough, for generation of terahertz waves through this femtosecond pulse. And that's why, more or less every lab, whoever starts working in terahertz or working in terahertz, they have this kind of detection or emission, basically source and detection technique, because this requires very less money. And also we get a decent amount of conversion efficiency. Okay, it gives a decent signal to noise ratio for our terahertz signal, and we can do our laboratory experiments with that. That's why this is really a nice technique. And in fact, we have been working with this photoconductive antenna. Also, we have a couple of antennas in our lab also. Okay. And then we have non-linear methods, optical rectification, for example. There are several non-linear crystals like zinc telluride, lithium niobate, gallium phosphide, gallium selenide, broadband. These are the different crystals. And this broadband bandwidth and high power is the beauty, the properties of the terahertz that we get. Okay, as compared to this technique is pretty straightforward. Only what you need is that you would need just a crystal, and they are available in the market also. You can just spend maybe 70,000-80,000 rupees to buy this kind of crystal. And then also you would need a femtosecond laser. As compared to this technique, this laser has to be a little strong. Okay. Power should be a bit high, like at least you would need 500 milliwatt power. And if you just hit this crystal with this kind of power, then you would be getting the terahertz pulses from the other side. You don't really need a alignment, very very really nice alignment and all that. You just simply, if you have a good power laser and if this crystal is there, then you can simply get the terahertz. And such systems are very easy to build. Okay, we have again this zinc telluride antennas with us, obviously, but we still don't have a high power laser. So our, we are doing our best, putting efforts to get such kind of laser. So this makes the experiment easy. And the beauty about that is that this can give you even broadband terahertz. broadband, this broadband means, when the bandwidth is pretty big, especially this this bandwidth will be pretty big. So, sorry, just 1 second. Okay, sorry. So yeah, broadband. Okay, yeah, this is broadband terahertz. So that's what we are means. The bandwidth is pretty big. You can have with this zinc telluride, at least you can have a bandwidth of like around 3 terahertz, and with gallium phosphide, I think 7 terahertz. Okay, and the power is also high as compared to the photoconductivity. And this is another semiconductor surface-based technique that is also used, and I have worked with, is the photodamper effect is used. In this technique, like indium arsenide is used, and basically when we hit this indium arsenide material, basically crystal, and when we are hitting with the optical beam, so it lead to the generation of carriers. And this generation and recombination of the carriers is in the picosecond time domain, picosecond time, and that's why when the pulse is gone, basically you would be seeing a terahertz wave. These oscillating dipoles will give rise to the terahertz waves. So again, it will give you large bandwidth. The crystal is a bit expensive in this area, and but this is very effective technique also. Okay. Then there is another technique that we have is the just 1 second. Okay, this another technique that we have is this 2-color mixing technique that is based upon the plasma. This one, and in this technique, basically we mix 2 colors. One could be 400 and another could be 800 nanometer laser light, both femtosecond pulses. And this BBO crystal is basically a doubler, frequency doubler, second harmonic generation takes place. And then, they can form a plasma over here, and through 4-wave mixing, this terahertz pulse is generated. The beauty about this technique is that, this can really lead to ultra broad bandwidth. Sometimes people have even reported, if they have very good detector, and 100 terahertz also they have reported. This is pretty broad, and you can do variety of things with this kind of thing. But again, with this kind of generation and detection method. But again, it would require a very strong laser so that you can create plasma also. So this is good, but at the same time, this is expensive technique, and also you need a lot of alignment and a lot of work that you have to do in getting this to work. Similarly, we have terahertz detectors. Okay, again the same antenna that we have, the same antenna that we have with the for the sources, and this same antenna can be worked for the detection also. The only difference in this case is that, in the last case when we had a source, there we had the femtosecond pulse hitting in, and on the other side we were getting terahertz coming out. But in this case, a weak probe laser pulse or femtosecond is made to hit in the gap. I will discuss in the next slide, and then basically simultaneously you are hitting the terahertz pulse. So this acts as a bias voltage and helps the detection. I will discuss in the next slide. And then we have other techniques of detection called electro-optic sampling technique. It provides more bandwidth. Okay, in this case also you have the terahertz as well as the femtosecond pulse hitting simultaneously. And when this terahertz wave, for example, if we have a sort of a crystal over here, zinc telluride it could be. So basically you have this terahertz wave hitting here, like you see this big terahertz wave field, then it has certain electric field. So what it does is that it will cause a change in the refractive index of this material, and when the optical beam is passing through this material, then its polarization will change. If it is this polarization, it may change to this polarization, and depending upon the change in polarization, it will show a variation in the intensity of light that is hitting the detector. and that intensity change can be recorded in the photodetector and through the lock-in amplifier, and we can indirectly know that what is the strength of the terahertz wave. Let me again remind you that terahertz waves are invisible. Certainly, they are infrared, far infrared wavelengths. Basically, they are, and that's why we cannot see them. And therefore, we have to be very careful in terms of developing devices, both sources and detectors, that we can get a sense of the terahertz without seeing them. We cannot see such waves, but we still have to detect them. Also, we have to use some indirect methods, like we have to measure the corresponding current and all that, if we want to make such detection and source generation techniques effective. Then again, this is air breakdown coherent detection technique. Again, here we have for a terahertz and an 800 nanometer light. They are mixed together, and then in this plasma medium, we get somehow the 400 nanometer light, and PMT used to detect that part. This is second harmonic light. This is also used for very broadband detection. And these are some incoherent detection. They will just tell you about the power. That's it. And they won't tell you the spectrum in terms of both phase and electric field information. They won't be telling. And this bolometer and pyroelectric detectors. Bolometer are a bit expensive because they would require some I would say cooling system. So that's why, but they are very precise. In pyroelectric detector, they are not that precise, but again, you can detect the terahertz with maybe just $1,000 or maybe 70,000-80,000 rupees money you can spend, or maybe a little more than that, to get such kind of pyroelectric detectors. But this at least give also a sense that you have some terahertz. If the system is not easily working, so you can get pyroelectric detectors to get a sense of the terahertz if it is there. All right, so let me discuss this terahertz generation via photoconductive antenna. Just 1 second. All right, so photoconductive antenna, I told you that is one of the least expensive, as compared to the other methods, is most effective and inexpensive method. So that is widely used in our labs. In this photoconductive antenna, we normally have a low temperature gallium arsenide. The gallium arsenide that is grown at maybe 600 Kelvin or so at low temperature as compared to the normal growth. So if it is grown, so low temperature gallium arsenide if we have, then as you can see, these are two transmission lines. They are of metal, normally gold. They can be fabricated in the clean room ambience, and these are the connecting pads here. We can apply the voltage over here. So there is a small gap of like 5 micrometer normally, and typically this gap is also like 100 to 150 micrometer. It will decide basically the center frequency of the terahertz generation. So when you are hitting it with certain light, for example, you are coming with a femtosecond pulse, and if you are hitting this gap, so what the femtosecond pulse will do is that it will generate carriers. Okay, if its photon energy is bigger than the band gap, then it will definitely generate carriers over here. And if you apply the voltage in this gap, okay, then what will happen that it will lead to a flow of the current, right? As the pulse is coming, as you see, then as the pulse is coming, more and more carriers will be generated, and more current will be there. Okay, and as the pulse is gone, okay, then this it will try to recombine, and then we will get the current reduced. Okay. So we will get a transient profile of this current, okay? And this transient profile of the current, will lead to the generation of the this time derivative of this current will lead to the terahertz electric field. Will lead to this oscillating dipole source or transient current. Will definitely lead to some sort of the electromagnetic wave coming out on the other side, and that will be terahertz, because this entire response that we are seeing over here, this entire response is basically in the picosecond domain. Okay, this response that is happening in the, this is the picosecond. So definitely we'll be getting the radiation because the acceleration and deceleration of these electrons, and we'll be getting in the terahertz domain. So this is how, you know, basically the photoconductive antenna work. And similarly, we have a detection technique. In this technique also, again, we use the same photoconductive antenna, but in this case, instead of, you know, having this biased voltage over here, we simply connect it with the ammeter. Okay, it will just measure the current. So in this case, what we do, in this case, we simultaneously hit this gap, this small gap, that is 5 micron gap approximately, with the terahertz wave as well as the femtosecond pulse. So the femtosecond pulse will generate carrier. This is this time a weak pulse. Okay, we can do it by putting some ND filters. This is a weak pulse. It will generate some carriers, but it won't move because we don't have voltage this time. So, but this terahertz, when it is hitting over here, it will act as a bias voltage, and corresponding to this terahertz, we will get the current over here. Okay, when we have the current over here, that current is basically measured, and this current will be proportional to this bias voltage, and that will indirectly tell us, okay, the terahertz wave is there. And this is how, you know, we measure the detection. We detect the terahertz wave on this antenna method. All right. So now, once we have the emitter and detector, okay. So emitter and detectors are basically put over here. These are two emitter and detectors, and this is entirely a spectrometer. We have, you know, different kind of spectrometer, absorption spectrometer, or maybe, you know, FTIR. Similarly, for terahertz spectroscopy, we have a time domain spectrometer. That's over here I'm showing. And in this time domain spectrometer, we definitely have terahertz emitter and receiver. But how the terahertz beam basically hit the terahertz, or we hit this terahertz emitter. So we have a femtosecond laser over here when pulses are coming from the femtosecond laser, and we have a beam splitter over here. This is beam splitter, and then it will split the beam into two parts. So, you know, normally the pump beam is 80%, and this is 20% normally. And when this is going to hit the terahertz detector, it is basically passed through mechanical delay. Okay, the role of mechanical delay is to adjust the delay between the probe beam pulses and the pump beam pulses. Otherwise, they won't be hitting at the same time. The detection won't happen. Okay, this delay is very important, and you have to adjust the timing in such a way that you both of them should hit this receiver at the same time. Okay, so once we have the terahertz emitter over here, you know, this femtosecond pulse is hitting here, and it will lead to the generation of terahertz pulses. Then these are two parabolic mirrors. Okay, parabolic mirror 1 and parabolic mirror 2. So in this, these parabolic mirrors are basically used to collect this and collimate it, and then again this another parabolic mirror will collect the terahertz wave, and then it collimate, or it again focus down to the terahertz receiver. And as I said in the last slide, at this terahertz receiver, both femtosecond pulse and this picosecond pulse, they are hitting simultaneously. Okay, and this time simultaneously can be adjusted with this mechanical delay stage. Okay, then it will basically lead to the detection. So normally, whenever we do the spectroscopy, we don't put the sample in between first in the beginning, and we just see that, you know, if we have a terahertz, and then once we are sure that we have a terahertz, then the sample is placed over here. Okay, and then again some properties, you know, some transmission profile will change for this time domain, and then again we will have a detection over here, and we will compare both the time domain signal to find out the information about this sample. This is a transmission approach, but sometimes, you know, this same approach is also used. As you can see, this same approach sometimes also used for these waveguide measurements. Okay, in the waveguide, these are two lenses, basically terahertz lenses, sometimes they are called, and these are two lenses, and then in between we have a waveguide approach, and these lenses do focus the terahertz to this small gap, and then it propagates through this gap, and then again it is basically collected by this lens, and through this parabolic mirror it reaches to the receiver. Okay, again, as I said that these are two emitter and this receiver. What is the beauty about this spectrometer, unlike FTIR or so, is that it basically measures the electric field, not the intensity. If something is being measured over here, we are detecting the electric field, means we are basically measuring its amplitude as well as phase. Okay, we can extract the phase information and amplitude information, unlike the X-ray, spectroscopy or whatever it's done. Because if we are measuring the amplitude, you can certainly know about the absorption feature. You can perform the imaging, and also when you are basically measuring its phase, then also you can extract the information about its refractive index. Basically, you can do the content information you can collect. Okay, that's what I was telling in my first few slides, that Terahertz has the beauty that it also can do the imaging, and also it can tell you about the elemental information, because we are able to measure the phase here. Okay, we are able to get the phase information, and phase information basically tells us how to get the refractive index information. So this is just one slide that I have tried to tell you that how the phase information basically tells about the refractive index information, and how the amplitude information basically tells us about the absorption information. So as I said earlier in the last slide, that first we don't have a sample and we do measure the transmitted terahertz, and then through the sample we measure the transmitted terahertz. Okay, then we compare both the electric field profile in this just 1 second. Okay, in this in this case we have this e to the power I basically we have this k into z, something like, or z is here d is the width of this thing, kd. Okay, and if it is refractive index is n naught simply. But in this case, when it is transmitted through this crystal, then in this case we have n. It won't be the free space n. It will be basically replaced by, in this case, n bar. Okay, and n bar is complex. It has a real part and imaginary part. Okay, and these two optical constants can be calculated by comparing the phase and by comparing the amplitude, as I am showing here. If you just compare the phase, like phase 1 minus phase 2, this is phase transmitted minus phase initial. Okay, then you can basically, if you subtract these two things, then you will automatically get this equation. Okay, so you can see that, by knowing the phase information, basically I can calculate the refractive index profile. This is very important information, because once we are able to get the refractive index information, obviously, then we are able to get the phase velocity, its group velocity information, its dispersion profile. All these properties, will help us to know a lot more about the sample. Okay, and amplitude information, as you see that absorption features can easily be recorded by this amplitude information, simply by comparing the amplitude, amplitude profile by Beer-Lambert's law. You can basically extract the transmitted amplitude information, and this will be the formula. By having this absorption coefficient, basically you can calculate by this transmission profile, transmitted terahertz. Okay, amplitude information or transmitted. So this is a very typical method that we use, a typical methodology that we adopt for doing the measurements for our terahertz sampling. Okay, so now let me come to the next part. Okay, in the next part is the waveguide. So as I so far have told, just let me take some water. All right. So about the waveguide part, just 1 second. Okay. About the waveguide, so I told you that if we want to come up with the terahertz technology, terahertz communication technology, basically, then we do need waveguides, definitely. And waveguides are essential ingredients, in any communication system. Okay, and we definitely need these waveguides, and waveguides basically are used for carrying information from one place to another. And in the microwave and in the infrared, we have waveguides available. Like, different waveguides, rectangular waveguide, circular waveguide, coax, and all that. These are very well-known waveguides that we have in the microwave. But why do we need waveguides? And especially some waveguide that we need is basically, if we want to develop a chip. For example, this is just a PCB for electronics, and just to give you a flavor of what do we want at terahertz, we just took this image from Google. So what is happening over here is that, information is being carried from one place to another. Okay, if we want to make terahertz devices, or maybe sort of terahertz electronics, where the information could be carried at a much faster rate, then we do need basically then we would need this kind of electronics devices, or this kind of devices, basically I would say, working at terahertz. Okay, and we would need this kind of signal propagation, or transferring signal from one place to another by on a planar surface. Okay, and therefore our effort is to get a planar approach, planar waveguide, where information can be carried from one place to another. Okay, and definitely if we can build these waveguides where the wave can be traveled from one place to another on a planar surface, that can basically ultimately lead to the this kind of complicated circuits for terahertz devices. Okay, but what are the challenges that we have? Well, normally, there are two things that we can use for making terahertz waveguides. Either it is metal or dielectric. Okay, so if we use the metal, then what happens that also I told you in the very beginning, if we use the metal, then metals basically strongly reflect back the terahertz. Okay, so if we are coming up with a terahertz signal, then it will just reflect back. So certainly it cannot be basically used for a waveguide approach. Okay, and if you use the dielectric basically either they are transparent. If we are coming with a terahertz, either they are transparent, it will be transmitted, or they exhibit strong absorption losses. So both these possibilities, in terms of developing the waveguides for terahertz, can be ruled out. Okay, as in a if we have a first glance, then we can simply say that okay, both these techniques won't work. Then how to construct the planar terahertz waveguides? Okay, then we have to definitely construct, and how to construct them, right? So this is something that we need. Then a lot of research in the other electromagnetic domains of this spectrum have shown that if we have a plasmonic waveguide, plasmonic approach, then maybe we can guide the signal. Like here the signal is there and it is being guided, it is being carried over here and here. Here we have a splitter, it is going over here and here. Some sort of structures are there basically. Okay. And like you see here, the splitters are there. You see. So this is a band actually. So if we have these, this thing, plasmonic approach, can we really build devices? Can we really have this thing working? So in that case, I'm sorry, I have to disconnect this thing. So yeah, this is a plasmonic approach. This is so this is a plasmonic approach that we have. So yeah, can we use this plasmonic approach for making the terahertz waveguides? So that's the something that I'm going to address next. If this is a plasmonic approach that I'm saying, then we have to understand what the plasmonics is first of all for the MSc people or maybe the newcomer to the research. So that's my next motive is that I'm calling them, this is a plasmonic approach. This whole approach I'm calling is a plasmonic approach, but what it is basically, and how does it help us in making devices? That's the next thing I'm going to do. Okay, so so just briefly in a couple of slides, I would like to tell you what is plasmonics, and then I will come back to terahertz plasmonics. Okay, so plasmonics is basically something that deals with the surface plasmons. Okay, with surface waves, and basically because this comes from the plasmon, surface plasmon, that's why we call it surface plasmons. Okay, and this is a new approach as compared to the previous generation approach. For example, you know, earlier what we have seen in the 20th century, electronic devices we have seen, you know, and also there was limitation in the earlier approach because we are every day trying to increase the speed of the device, and earlier we used to have number of transistors on a particular chip, and they are almost getting double in every 10 years. But according to Morse, he has said that basically a limit will reach. Maybe, you know, we are about to reach that limit. We cannot further reduce the size of those transistors, and definitely you cannot further reduce the size of the device. Definitely limit will come, and speed also that way will be limited at some point of time, but demand is always increasing. So this definitely have a Moore's limit approach, and also in the photonics approach we have a diffraction limit approach. You all know that, you know, we have a wavelength, then by lambda by 2 order you can build the devices, get the resolution. But if we are going to go down lambda by 2, then, you know, then the diffraction plays an important role, and we cannot reduce further the size of the device. But this plasmonic approach basically can also beat the diffraction limit, and also can also overcome the Moore's limit. Okay, and how it does that I will tell you in the next couple of slides. But overall, let me tell you that plasmonics is basically an area where we are dealing with the surface plasmons and its applications. Okay, what are surface plasmons? Surface plasmons are basically collective electron oscillations. Okay, they do propagate at the interface between a metal and a dielectric, often a vacuum. Okay, this is often a vacuum, but this is a metal and dielectric. Why do we need a metal and dielectric? When I will study when I will discuss this theoretical discussion I will have, then probably you will get this point. And the amplitude of surface plasma wave exponentially decay down. Okay, in both the media. This, as you can see over here, this is a movie. As you can see, this is propagating, right? And this is highly confined. Okay, this is propagating along this surface. This is not leaking out in the outer medium. And the field is very high at the interface. This field is very high as compared to the laser field if it comes and hit and reflect back. So as compared to that, this field is very high, and therefore it can be useful for variety of application, including material ablation, and, you know, in terms of getting non-linear properties, sensing properties, imaging, and so on. So variety of applications it has. But anyway, we will be looking its importance in the terahertz waveguide communication. So surface waves are basically highly confined to the surface. And in just 2 or 3 slides, I would like to discuss the dispersion properties. I told you earlier that dispersion properties are very important, because once we know the dispersion relation, we can extract the information about its phase, about its group velocity, about its refractive index, and so many things. Okay, so therefore I thought of discussing in a couple of slides about the dispersion relation. Okay, I think I have time. Maybe I can take half an hour more, hopefully. Okay. So in that case, so let me discuss the dispersion relation, a very simple dispersion relation that we have a metal and a dielectric, okay, region. So the field of surface plasma wave at the metal and dielectric interface are governed by the Maxwell's equations in both these media. We have a field over here, as I showed in the last slide, that here, over here, basically, we have a field like that, right? Okay. So this field basically, this is a mode basically, if I see that. So field of surface plasma wave is high over here, but it spreads in both the media, in the metal media, and let's assume it is a dielectric. It could be air also. Now let's assume it has a dielectric, and this is x is equal to 0, okay, at this interface. So in both the media, the wave propagation, the surface plasma wave propagation can be governed by the Maxwell's equations. In each the media, let's consider, this has a permittivity epsilon d, and this has a permittivity epsilon m in the x greater than 0 and x greater than less than 1, and then we can write down these Maxwell's equations in these 4 media, okay. And you know that if J is 0, I said there is no current also, no free carriers also. So if we have take the del, del cross of this thing and del cross of this thing, okay. Let me go to the next slide, and then we will be this will be something that will be getting, right? If you take the del product and if you solve it, and this will ultimately be 0, as I have placed 0, and minus del square. And this is pretty straightforward. This is just by solving third and fourth Maxwell equation, and you will get this kind of wave equation. Okay, that describes the wave propagation in the dielectric as well as metallic region. Okay. So now let me replace here. I'm replacing here with the relative permittivity epsilon by epsilon naught, and also mu r is equal to mu by mu naught. And if I do that, this wave equation I will get. Okay, it's very easy. You can do this analysis, and this is valid for both the media. So if epsilon r is replaced by epsilon d, then this equation is valid for dielectric media, and if epsilon r is equal to epsilon m, then this is valid for the metal media. Okay, so we have the wave equation for the dielectric medium and wave equation for the metal medium. Okay, and the metal permittivity can be defined by the Drude model also. Here I have neglected this losses, basically collision losses, but that part is also there. In that case, you can simply write omega plus I nu, okay, gamma basically. Okay, that should be playing a significant role also. So in that case, now I have the wave equation both in the both media. Now my next goal would be to solve this equation and this equation. If I do that, okay, let me assume that the variation for the surface plasma wave, let me assume that my surface plasma wave basically here have a TZ variation given by this. Okay, if it is the variation, then del by del z can be replaced by ikz, and also del by del t can be replaced by minus I omega, and this is exactly what I am doing with this first equation. Okay, del square E minus epsilon d by c square del square E by del t square. So if I do that part and if I solve it, simply, then ultimately this equation, because z term will be replaced by kz square, then I'll be getting this thing for the dielectric media, and when it is the metal media, then simply epsilon d will be replaced by epsilon m. Okay, here what I have done, I simply assume this term, okay, this term as alpha 2 and this term as alpha 1. So as you can see over here that because this is giving a variation in the x direction, that is away from the surface in the x direction, so definitely alpha 1 and alpha 2 represent the propagation constant in x direction, and also they basically give us information about the penetration depth in both the media. Later on we will see that part also. So this is alpha 1 and alpha 2, and now for this equation that earlier I have discussed, okay, if I write down the solution, Ez variation, as if I assume this is the Ez variation, and if this is the Ez variation, and similarly Ez variation for x greater than 0 and x less than 0. Again, because in z direction it is propagating, but in x direction the field should be decaying, right? I told you. So that is why in both the media this should be decaying. So here x is less than 0, ultimately this will be a negative quantity. Okay, and this x is greater than 0, this is a positive quantity, and ultimately the entire thing is negative. So means in both the media the field is decaying away from the interface. Okay, and if we apply the boundary condition, okay, if we apply the boundary condition, then certainly you can know by applying the continuity of the tangential component of electric field, then you will find out that A and A for the z direction, they are same. Okay. Okay, this then I will ultimately get these two equations from here. They are here, we are basically same. Now the next thing is that because electric field is finite for the surface plasma wave in the x direction, it has x direction finite component, and in the z direction. So z direction we have already found, and then let's find the electric field in the x direction. For that case, you simply use the first Maxwell equation, del dot E, okay. For this thing, you can use the first Maxwell equation, and this can be written, like this, okay. And then this Ez variation. Then simply you can substitute Ez variation from the last slide that we have discussed, and also you can integrate, and ultimately you can get the Ex component. Okay, this is for x less than 0. Okay, you can do this simple analysis. This won't be difficult. I think just a couple of steps. So I'm not really spending on each and every small term time on it. This is not irrelevant, but ultimately what do we get is that Ex and E, not irrelevant because of shortage of time, I would say. So this is Ex and Ex in the x greater than 0. Okay, this is one medium, this is second medium. So ultimately the overall field, if I club Ex and Ez, so I'll be getting my overall this thing. These are the electric field in x less than 0 region and electric field in x greater than 0 region. Okay. And if I again apply another boundary condition, continuity of epsilon, basically D, displacement vector, then I will get this dispersion relation. Okay. And if you remember, alpha 1 was basically kz square minus omega square c square epsilon m, right? This is square. And if I substitute alpha 1 and alpha 2, in alpha 2 it was basically kz square minus omega square by c square, and this is epsilon d. If I substitute these values, and then ultimately this is the final dispersion relation that we get. What is this dispersion relation? It is relating omega with k. Okay, let's try to plot. This is called the simple dispersion relation on a metal dielectric interface for the surface plasma. Okay, if I plot this one, so what do we get? If it is a metal dielectric interface, then I'll be getting, okay, I don't know why I'm not getting this thing. So if I get this, okay, so if this is, if this one corresponds to this thing, okay, this one basically corresponds to this one, okay, and this one corresponds to this one, okay, metal dielectric or metal prism interface. All right. So what do we see here? What we see here is that as the kz, the wave number is increasing, omega is increasing, and initially it matches with the light line. But after a while, what happens that after a while, at a certain frequency, maybe let's say this is the frequency, let's say this frequency, at point this one. So wave number, if we are able to excite surface plasma wave, that k of SPW, surface plasma wave, is bigger than k of light line. Okay. What does it mean? That lambda of SPW is less than k of 0. Okay, sorry, lambda of S 0. Okay, what does it tell? It tells you that can I just 1 second, because somehow my battery may be very low. So I'm sorry for this small step. So anyway, So what I'm going to do here is that lambda of SPW is smaller than lambda of my free space wave. Means that when I theoretically, this is what I have seen, that what I did is that I came with a light that was free space light, maybe a laser light, and somehow I got this to convert into surface plasma wave. That's an important question. How do we convert this thing? That we will discuss also. But it tells you that if we convert that part, okay, then our lambda gets reduced as compared to the light line. What does it mean? That I am now working with the low lambda light, low lambda surface plasma wave. Basically, whatever my diffraction limit earlier was, now it can beat the diffraction limit. I can get even better resolution. So that limit that was coming because of my lambda, initial lambda of the laser light, that limit is basically somehow is broken, or basically that limit is basically not applicable to this thing. Or we have some flexibility. So some important points again about this dispersion relation, exactly what I said, because in the last slide, as you have seen, that at a certain frequency, lambda of surface plasma wave is bigger than lambda of light. This gives lesser k of surface plasma wave bigger than k of light. This gives lambda of SPW smaller than lambda of light, and therefore it helps us in beating the diffraction limit. And also this time you can get better resolution because you have reduced the lambda, and therefore you can also miniaturize the devices, or you can make even smaller size devices. That is one of the beauty when we convert the laser light into surface plasma. Now another thing that I already told, alpha 1 scare, and this is another very important point that I'm going to discuss over here, is that we already got the dispersion relation. If you remember in last slide, this was basically minus omega square by c square epsilon. Okay, it was m basically. Sorry, this is square. This is nothing. So if you substitute that in dispersion relation, kz is equal to omega c by c epsilon m epsilon d whatever epsilon m plus epsilon d. Okay, if you do that, if you substitute in that equation, then basically in this last one, okay, sorry, oh, it's gone. Okay, whatever, like if you do alpha then if you substitute, okay, if you basically substitute kz is equal to omega by c into epsilon by 1 plus epsilon into half, and if it was epsilon d epsilon m, then you can have epsilon d and epsilon m. If you substitute, then alpha 1 will be coming out something like this thing. Okay, you can easily calculate that. And if since alpha 1 square and alpha 1 alpha 2 has to be positive, okay, then ultimate thing, if they are negative, then this entire thing has to be negative. Okay, and this is what I'm telling over here. So now you see that this can only be negative if epsilon m is negative. Okay, that's why I was saying that why do we consider metal? Because one metal and one dielectric, because it ultimately leads to a negative epsilon m. Okay, for the generation of surface plasma wave. Okay, and at high frequencies, as you know that this is epsilon m. Okay, if you substitute this value in this one, okay, in this one, then ultimately I'll be getting omega is equal to omega this sc, okay, omega sc will be less than or equal to, this is equal to omega p by, so this is the cutoff frequency. What is this cutoff frequency? This one, omega sc, this one. This is the cutoff frequency. This is the maximum frequency that is allowed. Okay, all right. So now the very important point, the next point is that when frequency is very low, basically when we are over here, okay, when we are over here in this region, frequency is very low, or omega is less than this entire thing, omega of sc. This is omega of SC. If this is very low in this region, then ultimately from dispersion relation, if you substitute these values, and since this is much bigger, so ultimately this and this term, basically they become dominate and they become cancelled one, and ultimately you are having this phase velocity that is exactly of the light line. That's why in the beginning they are matching with the light line. Okay, and also alpha 1, alpha 2 we have already calculated. Okay, and if you again alpha 1, alpha 2, if you do calculate it that way by substituting the dispersion relation, then these are the values that we will get. Okay, and since omega is less than omega p, and by this thing basically less than or equal to, and then ultimately it gives that alpha 2 is less than alpha 1, means alpha inverse 2 inverse is greater than alpha 1 inverse. Okay, what does it mean? That the penetration depth inside this medium is less, and in this medium, in the two medium, this is two medium, this is my one medium, it is more. That's why, you know, surface plasmons, this theoretically also it tells you that the surface plasmons have lesser penetration in the metallic region and more penetration in the in the air region or dielectric region. Okay, so these are some of the properties. Okay, now the question comes that if normally in the ordinary case, question comes that can I really excite surface plasmons by coming from here at the top? Because I already told you that dispersion relation, I already told you that K of SPW is bigger than K of 0. So now if I am coming here from the top, then certainly K naught sine theta, okay, K naught sine theta would be K of SPW has to be equal, right? This term K naught sine theta should be equal to K of SPW. Okay, if I take the component, then this will give sine theta K SPW by K naught, sine theta is less than 1, so this will give this thing, but this is not true. Okay, for this case this is not true, so that's why, you know, you can't just come with any light and hitting on a surface and you can excite surface plasma. No, that's not possible. Okay, I mean, you may have a laser light, then it will come to the metal and it will reflect back. That's what it's telling. Okay, you have to devise a mechanism that will basically couple the light to surface plasmon and then go back, and that's why normally a Kretschmann configuration used. And if we are passing this light, this is called Kretschmann configuration basically. Okay, this is Kretschmann configuration. Kretschmann configuration. So in this case, the light is brought from the back of this, not directly from the top, from the back of this prism. Okay, from it is entered through a glass, and this glass refractive index basically helps us in compensating this wave number. Okay, if we are coming from the glass light, then K parallel would be equal to this thing, and since SPW is this one, if we compare both, and then we will get this value, this equation. And in this equation, if you substitute all these parameters, then I will get sine of theta p is equal to 0.71, means it is feasible. So what I have shown here briefly is that if I am coming from the back side of this prism, then definitely by, you know, putting some genuine number, definitely it is possible that this dispersion relation can be satisfied here at the interface. So means, you know, by putting here at the back, we can satisfy this dispersion relation. But then how it is experimentally done? That is very important in Kretschmann configuration. Experimentally, what people do that they come up with a light, you know, they keep on varying this angle, as you can see here. But at a certain angle, okay, this undergoes a sharp decline. As you can see, a sharp decline. It's in the reflected light. We have a detector here, and we are detecting here. There is a sharp decline in this dotted region, as you see. Especially when it becomes dotted, at that point of time we have a sharp decline. At that point of time, this energy is transferred to these electrons in this thin metal layer, and they lead to the surface plasma wave at the metal dielectric interface or metal air interface. And this angle is basically called as the Kretschmann angle, or sometimes called surface plasmon angle, or attenuated total reflection angle, because at this point of time, there is an attenuation in the total reflection. All right. So anyway, this is simply about the surface plasmons. Now the question is that, okay, this is fine, but if it is metal, and if we are dealing with terahertz, but I told you that in terahertz we simply reflect back. So can we still excite surface plasmons at terahertz using metals? Simply no. But in principle, if we devise a mechanism, where it can compensate the wave number, then yes. But how do we do that? So you can see here, there is another method. It's called a grating method. Diffraction grating is built, with this, diffraction grating is built, and then this wave number is such that, it will, this one, K parallel component from this thing, this is the K parallel component. And if diffraction grating is chosen in such a way that it can satisfy the dispersion relation or the wave number of surface plasmon, then also this is possible. But we have to be very careful in designing this grating. So this is what we do in the terahertz, exactly. And this was actually first proposed by or shown theoretically by Sir John Pendry. He had shown that if I corrugate my metal, if it is not corrugated, it will just reflect back, asymptomatic behavior. If it is corrugated, then he showed basically that you can, in fact, provide some sort of skin depth, and by solving Maxwell's equation and all that, he in fact showed that this can lead to a surface plasmon dispersion relation, exactly the dispersion relation that I showed you in last couple of slides. This dispersion relation is not calculated the way it was calculated earlier, but if you see this dispersion relation, this looks exactly same, okay, at least similar to that one. But here the properties where it will saturate or where it will, how it will show a profile, this kind of thing, that can be controlled by these corrugation parameters. So this gave us the key to make some terahertz plasmonic devices. In the next slide, I'm showing one or two slides or so. I'm showing some of the work that I did in the very beginning, experimentally. What we did actually, we took a stainless steel, a metal basically, and this is the metal region, and we corrugated it through laser micromachining by certain, these are the certain parameters, and we corrugated them, and we made a 8 centimeter long waveguide. And somehow we brought this terahertz radiation to this structure. This also requires some hard work basically, how to couple the light free space terahertz radiation to these structures. We basically used a semicircular groove. And we found that semicircular groove basically, if you are hitting terahertz over here, then it basically concentrates over here in the center. This concentrate on the center, and then once it is, we place our corrugation starting from the center, it start propagating to the other side. And this electro-optic method we use for the detection. We placed our crystal at different places, here, 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 to just see different properties, okay, to check if waveguide properties, okay. And we in fact found that basically it do lead to the propagation in a highly confined manner. But this is again a challenge in experiment, that because if we are calling it a waveguide, wave should be confined. Wave should always be confined to this region only this region. It should not spread. My wave starts from here. It should not spread to this region or this region, right? It should remain confined. So we had to check electric field in this region, above from this region at different processes, whether it remains confined or not. And for that also we had to change the entire spectrometer setup that time, and we came up with this modified setup where the beam is coming from the top, it is hitting the semicircular groove, and somehow it was focusing over here and it was propagating to this side. So in this case we can move the entire this setup to this side and that side, so we can do measurement in the transverse direction. We can move it upward and downward, so we can do the measurement in the upward direction. Basically, by modifying this setup, we were able to do this measurement for the waveguide. And again, for this kind of setup, because this was done at my postdoc level, and we used to have very sophisticated laser system. One is shown over here that I used, and this kind of measurement is only possible with this sophisticated setup. You cannot simply use the photoconductive antenna base. This won't be probably working, okay, in this thing. So anyway, just a flavor, how did we do that? So again, I'm showing here, once we were able to couple our free space terahertz to this waveguide over here, then it propagated to the other end, and we placed our detector over here, and then we saw that what is the profile. This was the broadband signal that was hitting here, and on the other side, we found that basically only certain frequencies are propagating. This frequency, and this frequency. And through simulation, we checked what they are. And we found that when we tried to check the profile of these modes, of these frequencies, then we came to know basically that they are showing different profiles. And that's how we called them at 0.3 terahertz. It's a fundamental mode, this as a second order mode, and this as a third order mode. So this further, vindicated the fact that, different modes are propagating along this waveguide. And this is how all these modes propagate together. And we did some more measurements in terms of, getting this loss information, their confinement in the transverse and in the lateral direction. So we did more calculations by putting some sort of, as I said earlier also, for loss measurements, we placed our detector here, and so on. And for transverse measurement, we placed our detector here, at different places. And we found that basically it is confined here in loss measurements. This is the loss measurement in Z direction. This is this is transverse direction. Also, we moved our detector at different position out from the this thing. In Z direction, we were able to show that within this 1.69 millimeter on the order of wavelength, we were able to confine the terahertz. If corrugation is not there, this was about 5 millimeter. Okay. And full width at arc maximum, also we found that it is pretty much confined to this region. Field is pretty much confined to this region. And also in terms of loss, we see that, where 36% of signal is left, at that point of time, it was propagating to 14 centimeters. That was a very good distance. So basically, it was acting, this structure was acting as a waveguide. So that's the beauty about this thing. So basically, we feel that this kind of approach can be used for making the waveguide. So this is the last slide that I'm showing here. So this is a simulation picture, as you can see here. Once we are coupling light through simulation, as you can see here, my signal is propagating along this corrugation. Okay. If I change the direction of this corrugation, then definitely my corrugation, my wave propagation will also change in that direction. So basically, it is telling that by designing these structures on a planar surface, I am able to control the direction of the propagation of my surface plasma. I'm intentionally showing here the band. We did it on the straight waveguide. Straight waveguide was pretty easy to show, but in the band there are losses associated with that, and that's why we thought that if it can propagate through bands, and normally in the circuit board we have some bands. Okay, we have some splitters. We in fact demonstrated some splitter also. So this is just a band where we had a 45-degree angle band. So whenever it finds a structure over here, it couple in this direction, it couple in this direction. If I further bend it, then it will make propagate in different direction and so on. So this kind of approach can be basically used for making the devices on a planar surface, terahertz devices, and this is done at terahertz frequency, by the way. Okay. So this is a promising approach, obviously, by corrugating the surface. And corrugation properties, this is a specific mode we have detected at certain frequency at 0.3 terahertz. But if I change the frequency of the different mode, then I can also propagate different mode. And these mode properties can be controlled by the dimensions of these corrugations. Okay. So this anyway, this approach is a beautiful approach that we have seen that, okay, this can be basically useful in making terahertz circuits on chip devices. Anyway, in conclusion, the terahertz waves have potential to build next generation components such as sensors, imaging systems, and high-speed communication devices, as I showed here. Okay, they can basically lead to terabits per second data transfer, and for that we would certainly need planar waveguide devices, and that's what I have shown here in the very end. Apart from the introduction of terahertz and plasmonics, and in that direction, plasmonics approach is one of the very promising approach for propagating terahertz waves on a planar surface in highly confined manner. It can be basically used for making miniaturized devices. Obviously, we need to work a lot in this direction to develop this terahertz technology for high-speed communication. This is just a waveguide approach, but I think we need to come up with devices such as, like, like electronics we have, transistors we have, something plasmon transistors or something like that we need to develop if we really want to make it a full-fledged technology. And for this particular work, I have a group of people. In fact, this is old slide. I need to add one or two more people. Sorry, this I could not update, because this work was done, plasmonic work is being done by my two students, basically this and this collaborator. He's my student, in fact, and who is working here in a university. So plasmonic work is being done, but in terms of collaboration of the other work, we have been collaborating with Professor Devendra Mohan, and also with the TIFR also, in terms of doing some experiments. And I have few more people that who are working in my lab. And also we have vacancy for the PhD positions in our group. And also you're always welcome to come to my group for the internship position. Thank you very much for your kind attention and for being patient, to keeping patience in listening my talk. I hope I didn't bore you.
Oh. Thank you, Dr. Gagan, for very much thankful to you for accepting my offer to give the talk on terahertz plasmonics. And you have, in fact, given the insight of terahertz. Basically, you have taken all the mathematical equations and given a classroom lecture, which was the need of these participants. So terahertz for ultra high speed communication devices is need of the hour that we are looking for in this world now. And terahertz detection you have also covered, and particularly in this COVID time when we are talking on the virtual platform, and you have very well demonstrated each and every concept of terahertz plasmonics. So nothing better than this lecture could have been, and I have heard the very fantastic lecture after some time. So thank you very much, and we'll keep on collaborating. And I invite the genuine researchers or the genuine faculty to interact if they are interested in this area of photonics, and they can now understand that the field of photonics has evolved so much that there is a lot of scope as well, and we can do a lot of work in this area. And this is the future 21st century, as has been said, it is for photonics, and various fields are evolving now. So with these words, I once again thank you, Dr. Gagan Kumar, for joining us. And now for the participants, it is an announcement that we'll be meeting sharp at 3, and there is a lecture by Dr. Amitva Ghosh. He has been from IRD Dehradun, so his talk will also be a very good talk. So
yeah, thank you, sir. Thank you very much, and thank you all the participants, audience. Thank you again.
Thank you. Dr. Gagan, can we have the acceptance from you if we put the lecture on YouTube?
Yeah, no problem, sir. I will be happy if people get.
Yeah. Thank you very much. We have already recorded it, and it will be done.
Yeah. No
Thank you.
Yeah, if you guys have any questions, queries, I welcome you, and you can always write email to me. You can also check my Google profile, Google Scholar profile for my recent publications. And I would be happy to answer things, and also for short-term visit, if people are interested in terahertz plasmonics, I would also appreciate, and I will respond. Thank you, sir. Thank you again.
Thank you very much. Thank you.